Welcome back to our workshop, day 2. So today we'll continue the topic theory of radioactivity that Dr. Savisaj Patragaru started yesterday. Now the first session will be theory of radioactive decay part 2. So now I welcome Dr. Savisaj Patragaru to continue his talk.
So welcome to the second day of the technical session. So as we discussed yesterday, may I have that pointer please? So we discussed yesterday a few things to understand that what radioactivity is in general. We discussed the concept of radioactive decay, concept of half-life, and then concept of parent-daughter decay, and then daughter growth, and then also the radioactive equilibrium, right. So far then we understood that all the nuclei are not stable, some of them are thermodynamically unstable and wants to attain stability by modes of radioactive decay. Okay. So let us focus on this lecture. I kept the learning objective in only one line, that let us try to get a insight of why nuclei become radioactive. Okay. So by the end of this lecture we will have a reasonable understanding of why certain nuclei are radioactive. So I will be discussing these nuclear properties like the structure, binding energy. I will touch upon very briefly some of the nuclear models, and then I will be very briefly again touching upon this alpha, beta, gamma, fission, different modes of radioactive decay. Okay. So as we say that nucleides which do not change with time, okay, like we know many chemical elements we see in our periodic table. At the same time, in yesterday's nucleide chart, as we observed the black lines which is passing through the center, I called them to be stable radionuclide. But why all the nucleides are not stable? That is the question. So certain combinations of neutron and proton do not remain in the same configuration due to instability, right. I told you yesterday, like if you have excess of neutron or if you have excess of proton, then what is required to attain stability? Then either proton or neutron they wants to interchange, and then they try to reach to this black line to attain the stability. So the final goal is to transform to stable nucleides. So again, let us look back into the little bit of history, that how the concept on the structure of atom actually evolved. That again you all know this, because this we all study in 11th 12th standard of physics or chemistry. Like you all know this Democritus, who is a very renowned Greek philosopher, who first gave us the idea of this atom, who proposed the concept of indivisible particles called atomos. So atomos in Greek is basically indivisible, and then after a long time the first atomic model came by Dalton, who introduced the atomic theory, who described the atoms as indivisible spheres with unique properties for each element. You see, this kind of solid sphere he assumes. In Dalton model he does not talk of anything else, he just say that it is solid indivisible sphere in 1803. Now again, as you can see, almost 90 years of wait. After almost 90 years of wait, that time, as I was telling you yesterday, this Becquerel discovered radioactivity. Okay, and once Becquerel discovered radioactivity, it was revealed that some elements spontaneously emit radiation, which challenge the idea of Dalton, who imagined that atoms are indivisible, because the radiations are coming out like alpha, beta. So then atoms must not be indivisible, and a study on subatomic particles actually began. Now, at the same time, of course, this Thomson discovered the electron, that is the negatively charged subatomic particle, and which is 2000 times lighter than hydrogen, and is proposed the plum pudding model. You see, this plum pudding model of Thomson is very interesting. So, those days it was believed that this atom may be a kind of a pudding, where you have, like, you know, the plum or this that you add, no, cherries or plum, they are actually uniformly distributed in this pudding matrix. So, for example, this kind of thing where the negatively charged electrons is embedded in a positively charged soup homogeneously. But then the question that was a natural curiosity those days was how the positive and the negative charge they distributed in the atom. Okay? And in that line, in 1909, there was a remarkable experiment by Rutherford. I am just going to show you in detail in a couple of slides later, but you can see this Rutherford, who actually did a gold foil experiment that led to a very, very fundamental discovery of the atomic nucleus, which disproves the concept of that plum pudding model. I will tell you the Rutherford model a little later. Let us first finish the history. Then Bohr developed the Bohr model, which suggested that the electrons actually orbits around the nucleus, and then in 1926 Schrodinger proposed the quantum mechanical model, which then treat electron as existing as in a probability cloud. So, the concept of orbitals was introduced after introduction of this quantum mechanics, and then Chadwick, who discovered neutron, it's completed the understanding of the atomic nucleus, okay, kind of. So, if you look at the systematics of the stable nuclide that is available, you see we have two different kind of nuclide. One could be even mass number nuclide, another could be odd mass number nuclide. Now, this even can be achieved by even Z even n or odd Z odd n combination, and odd can be achieved by even odd or odd even combination. If you see that 165 stable isotopes are there for even even. So, the even even systems are the maximum stability compared to the other. So, what is the reason for this extra stability for the even even isotopes? So, it is understood that it is the pairing among the neutron and proton which actually brings this extra stability for the even even isotopes. And for even Z, at least 2 stable isotopes. For example, for tin it is 10 stable isotopes are possible. For odd Z, often 1, never more than 2. Similar thing is true for neutron also. For 7 stable isotones, for n equals to 82. So, this extra stability that was observed for this neutron or proton at these numbers 2, 8, 20, 28, 50, 82, 126 like this, they are called the magic numbers, because those days it was not well understood that why they are extra stable. So, there is some magic. So, these numbers actually are called magic numbers. And then if you look at that, more than 85% of the earth consists of the even nuclide. So, if you look at this our earth composition, for example, we have around 48 weight percent of oxygen, which is basically even nuclide. We have around 26 weight percent of silicon, that is 14. So, you can see that the even nuclide are having a very good yield in our earth. So, here we comes the Rutherford experiment that I was telling you just a few minutes back. What was done is that Rutherford was working on alpha particle, and he took a gold foil, thin gold foil, and incident this alpha particle beam on this gold foil, and he just put a fluorescent screen surrounding to it, so that he can detect any alpha particle coming from any direction, okay, in that. So, for example, when he was doing this alpha particle interaction with gold, he was, because the momentum of the alpha particle is very high, he was expecting like all the alpha particle, had it been the Thomson plum pudding model, all the alpha particles majorly should actually transmit through this thin gold foil beam. But to his surprise, what he observed is most of the alpha particle passed through, but a few got scattered at large angle. So, it was quite the most incredible event. It was almost as surprising as if a gunner fired a shell at a piece of tissue and the shell bounced right back. You just imagine the observation by Rutherford, and it was published in those days in Philosophical magazine in 1911. So, you can see that had it been the Thomson plum pudding model, the alpha particles should have been puffed through, but Rutherford observed that some has been scattered back. So, he proposed a model that the majority of the mass in a given atom must be localized in a very small volume, and that is why this small volume is responsible for the scattering of this incident alpha particle at larger angles. Okay. So, he came to some conclusion that most of the space in an atom must be empty, and then the mass is concentrated at the center, also it is positively charged, and the ratio of nuclear and atomic radii is around 10 to the power minus 4. So, with this observation he gave the concept of atomic nucleus, and he said that the nucleus are at the center of an atom, which is similar to, you see that according to the dimension, the nucleus dimension is similar to a football at the center of a football ground. You imagine that you have a big football ground, inside that if you have a football. So, compared to the overall atomic dimension, the nucleus is like that, like compared to a football ground, it is just a football. So, how do you actually give notation of any nucleus? Like for example, you can write it like this. Let us say the X is the element, and this A is the mass number, this Z is the proton number or the atomic number, and this N is the neutron number. You can also write it like this, that simply AX, where A is the mass number, X is the atomic, X is the element. So, once you write the element, Z is fixed. Once you have the Z is fixed, A is known. So, you can anyway know the N. So, you can simply write it like this also. And there are few definitions which you can just go through, that there are isotopes, there are isobars, there are isotones. Isotopes are those who have the same proton numbers. Isobars are those who have the same mass number. Isotones are those who have same neutron numbers. And there are nuclear isomer which have nuclear excited states. So, same atomic and mass number, but in different excited states. So, here comes the concept of this nuclear density distribution. If you carefully look at this graph, you can see the y axis is nuclear charge density and the x axis is nuclear radius. So, what you can see, this was first determined by kind of electron scattering experiment, where a very high energy electron was used to do some scattering experiment over these atoms, and it was found that the nuclear radius is never a sharp boundary line, but it has some kind of diffused boundary, because nucleus does not have a sharp boundary. So, what was observed, that around 4.4 A, so it is related to like this, that the skin thickness, this is called the skin thickness, at which that the charge density falls from 90% to 10%. So, this boundary is defined as the skin thickness, which is basically 4.4 A, and you see that radial distance between 0.1 rho 0 to 0.9 rho 0, and this rho r is basically this kind of Fermi function was defined, was able to define this kind of charge density behavior in nucleus. And the distribution of the charge density is neutron distribution is similar to the proton distribution. So, if you look at this for various other nucleate systems, so if you see from carbon to oxygen, to nickel to lead, if you see that obviously because you are going to heavier and heavier system, so your nucleon number is increasing, so your nuclear size is increasing, but very interestingly your skin thickness does not change much. Okay. So, it is only the nucleus is getting heavier, so your size is increasing overall, but the skin thickness does not change much. It for all the systems, the skin thickness is around 2.4 femtometer. Okay. And that says that the radial charge, that says that the distribution of the nuclear matter is very similar to that of the nuclear charge, and in all the systems the nuclear charge density, they remain kind of same. So, the constant nuclear density, and this actually points to the presence of short range nuclear force. Okay. So, let us see, like for example, as you all know very fundamentally, volume is mass per density. So, if the density is constant, So, volume is proportional to mass. So, I can say by little bit of calculation that the nuclear radius I can write it like R0 a to the power 1 by 3 femtometer, where R0 is basically 1.15 to 1.4 femtometer. So, if you do a very simple calculation for 27 aluminum as a test example, you can write the mass of this 27 aluminum as 27 into 1.667 in 10 power minus 24 kg, and then by the volume. So, if you just proceed with this simple calculation, you can calculate the density of this nucleus is around 10 to the power 14 gram per cc. Now, imagine 10 to the power 14 gram per cc is a huge density, because the density of aluminum is how much? Around 2.7. Around 2.7 gram per cc is the aluminum density in general, aluminum metal density. But if you see the aluminum nucleus density is 10 to the power 14 gram per cc. So, that actually corroborates the fact that the nucleus is very dense system, and the nuclear density is very high, extremely high. So, what type of force is holding this such a high density together? Like, so it definitely must be attractive, must be short range. So, very strong force. This is defined as nuclear force. Okay. So, going to very briefly further details, like how actually such a strong force is basically possible between the protons and neutrons. So, it was those days conceived the idea that although these neutrons and protons we assumed initially to be their fundamental particles, but they are still not fundamentals. They are actually consisted of even fundamental particles called quarks, and basically this interaction between the quarks is responsible for such a strong interaction between the neutrons and protons, and which give it the enormous stability and the high density. Now, let us look at the concept of binding energy, which is a very interesting concept that measures the nuclear stability. So, the energy released in the formation of the nucleus from its constituent nucleon, let us say this is the nucleon, I can write it like the mass defect. So, what is mass defect? Let us say I just take the mass of n number of the mass of a minus z number of neutron plus the mass of z number of proton minus the mass of the nuclei. If I do that, it never be 0, it is always giving me some positive value. That shows that once you combine all the nucleons together inside a nuclei, some energy is released. Okay? So, some energy is released, and that energy is basically the binding energy. So, it is basically coming from this mass defect, the difference in the mass. So, the binding energy is basically mass defect, and then you can convert the mass into energy, as you all know from Einstein's famous equation, mass energy conversion. So, if I simply multiply this mass defect with this 931.5 MeV, I get the binding energy, and so if I do this binding energy per nucleon, it gives me the measurable a characteristic property of a given nuclei. So, let us look at this curve. This is a very popular binding energy curve. So, if you look at this curve, what you can see is that it has some kind of shape, but initially it is very sensitive to Z or A, but after that it is kind of flat with a slight decrease. So, let us read our observation that the curve is relatively constant except for the very light nuclei, and then the average binding energy of most nuclei is within 10% about 8 MeV. Okay. So, in this region the average binding energy is around per nucleon is around 8 MeV, and this curve reaches a peak around A is equal to 60, where the nuclei are most tightly bound. So, with this observation, what we see here with little bit of further observation, if you see that you have the maximum stability around here, this iron, okay, and this corroborates with our general observation that in our earth crust also you will see that we have this maximum number of stable elements present in this region. We have a lot of iron in our earth crust or surrounding any elements. So, that is basically because the stability in this top is the maximum. So, if you are either left side of this binding energy curve or the right side of the binding energy curve, you actually tend to climb this hill. Okay. So, once you are on the top, so everyone, suppose you are here, you also wants to go there. Now, if you want to go there, you have to undergo nuclear fission, or if you are here, you also tend to go there by nuclear fusion, and by this two mechanism you actually release energy. Okay? So, that is why we can get energy either by nuclear fusion of this lighter elements isotopes, or we can release energy by the fission of the heavier elements. Okay? So, by both the mechanism we can actually climb the binding energy curve and liberate nuclear energy. Okay? That is why you heard that the either fission reactor concept or fusion concept, okay, to get energy. So, we can gain energy in two ways, as I just discussed, by either nuclear fusion or by nuclear fission. Okay? So, for example, you can do this DT kind of fusion reaction which release energy of around 70 MeV, or you can have a nuclear fission reaction with this neutron bombardment of uranium which gives you energy of around 200 MeV. Now, again, why the binding energy curve looks like this? Okay, this was just observation, but why it looks like this? In order to understand that, we have to little bit now enter into the nuclear models, which says that let us try to do the calculation of binding energy, where you can see this binding energy is basically depending upon many different terms, what we call like a volume energy term, surface energy term, Coulomb energy term, asymmetry term, and a pairing energy term. So, what you can see, let us look at this graph, very interesting. Let us say my binding, a given nuclei is having a number of nucleons in it. So, binding energy per nucleon would have been this kind of flat response if this strong nuclear force is the only reason for this giving the binding energy. Then my binding energy per nucleon curve should have been this flat, the first line. But then it was realized that as we are going to bigger and bigger size nucleus, my surface area of the nucleus is increasing. So, as the surface area of the nucleus is increasing, it is bringing some instability. As you can imagine, now we used to play with the soap bubble. So, as the soap bubble actually keep on expanding, after a given time it explodes because the stability actually decreases. So, like that also in nucleus also, if you are going to bigger and bigger in size, okay, its surface energy is bringing some distability. So, the surface energy correction term we introduced as a negative correction term, and that too also the Coulomb energy is also destabilizing because the number of protons is increasing. So, the Coulomb energy term is again further decreasing stability, and then it comes the asymmetry energy terms. So, this is between the difference in the numbers between the neutron and proton, they actually bring some instability parameter based on their asymmetry, and then there is a pairing energy term. So, somewhere it is neutron-neutron pair, unpaired. So, the final curve get a shape like this, and these parameters are basically called semi-empirical parameters. These are basically obtained by semi-empirical approach, like by fitting the observed binding energy data for a large number of nuclei. So, you will see that it is kind of nonlinear least square fit parameters, and because they are obtained semi-empirical way, so they are called semi-empirical parameters. So, it gave us the liquid drop model, which actually provides a conceptual framework for understanding nuclear binding energy by considering the nucleus as a drop of liquid. It incorporates terms that represent the volume effect, surface effect, Coulomb repulsion, etc. But here the assumption was that nucleus is like a droplet of incompressible and homogeneous liquid. All nuclei have the same density. Interaction between nucleons is strong. Nuclear force is charge and spin independent. So, proton-proton, neutron-proton, proton-proton interaction, they all are same. Okay. It is strong and attractive. It is short range and effective amongst neighbors. Each nucleon interacts with all its nearest neighbors. So, if we look at little bit more detail, like the binding energy semi-empirical equation that we observed. So, I know the mass defect formula, that the mass Az is Zmh plus Nmn minus the binding energy, and if I just use this binding energy formula from my semi-empirical mass equation that I just showed you few slides back, and then if I simplify, I will be seeing that I am able to do this kind of separation, like for all the z squared term, for all the z terms, and for all other terms, I just separate the variables, and it actually get a form like this, which you can see if I then plot this m by z, it takes a parabolic shape. Okay, where this alpha, beta, gamma, delta, they are all called local constants, which is basically is having a form like this. So, this is a little bit of mathematics that you can actually try to solve, but you ultimately get this kind of a form. So, in a family of isobar, if you see that the mass is represented by a parabola of m versus z. So, at the at the minima of that parabola where you have this del m del z 0, you can solve the z of maximum stability. Okay. So, the z at which the energy is minimum. So, as you see it takes this kind of shape. So, for example, if it is odd mass number or if it is even mass number, you say that there are shapes like this, parabolic shape, and you can see that this is the z of maximum stability or the z mean. So, for a given mass number, there is some z which have the maximum stability, and that is your zs or z of maximum stability or z mean that I just did. And from this, suppose you have an isotope here, it has a tendency to undergo beta minus decay to reach here. Suppose you have something here, it has a tendency to undergo beta plus decay to reach here. Suppose you have something in this, here also you have two parabola because here the pairing terms comes in. So, depending upon the situation, either it is plus delta or minus delta. So, you have two different parabola, but here also if you tend to get from left hand side to this bottom or the right hand side from this bottom, you can actually undergo beta minus or beta plus decay. And here another event that also you can just see, that sometimes you may observe the double beta decay also, like for example, if you have here. So, from here you can also there is a probability that it can directly reach to this z of maximum stability by a double beta kind of decay. Now, the certain things which actually liquid drop model could not explain, although the liquid drop model explained many things, but certain thing it could not explain. So, it fails to explain the magic numbers of the protons and neutrons that was observed. Okay. And the greater abundances of isotopes and isotones for the magic number, it was not able to explain. It cannot accurately explain the isotopic dependence of the binding energy. It does not provide any insight into the spin of the nucleus. It fails to describe the excited states of the nucleus and the transition between them. And while the model can explain the general fission process, it cannot explain the detailed mechanism of fission, such as how a nucleus deforms and splits into two smaller nuclei, or the specific formation of fission fragments. So, for example, if you see here, these doubly magic nuclei are especially stable, and also if you see this mass numbers such as 4, 8, 12, 16, 20, when you closely look at the binding energy curve, the liquid drop model actually does not explain this. So, the concept of this cell structure then slowly evolved. So, how it was began is like, for example, you can see that atomic cell structure was quite well known by then, right. We already had the concept of this Bohr orbit and all. So, we knew that the atomic theory based on the cell model provided us the complicated detail of atomic structure. So, we understood the existence of very stable noble gases. So, nuclear physicists also therefore attempted to use the similar theory to explain the properties of the nuclei that were observed those days. So, in atomic case, the potential is supplied by the Coulomb field of the nucleus. So, in atom what is happening? The nucleus is at the center and you have the electrons outside the nucleus. So, all the electrons are experiencing a potential which is provided by the nucleus. But what is different in a nucleus? In nucleus, you see all the nucleons are within the nucleus. So, it is like in nucleus no such external agent exists to give its potential, but the nucleons they move in a potential that they themselves create, right. So, in a nucleus it has its own potential, and inside that nucleus whatever nucleon is there, so each nucleon experience its own potential within the nucleus, and the motion of a single nucleon, it is governed by a potential caused by all of the other nucleons, and this gave the basic assumption of the cell model. Just to give you a very brief glimpse like how in atomic model this concept of cell actually witnessed first experimentally. For example, if you see this the atomic ready versus Z curve or the ionization energy versus Z curve, you can see that at certain Z value there is a certain jump of the value that gave us that gave first indication that there must be something which is happening at this Z value particularly, so that the atomic radius is changing abruptly or the ionization energy is changing abruptly. So, the atom must be cell structure. So, similar to that line in nucleus also similar experimental observation actually observed. If you look at here, it is the plot of the difference between the measured value and the predicted value of the proton separation energy and the neutron separation energy as a function of nucleon number. what you can observe is that, what you can observe is that at these nuclear number, like when it is 8, 20, 28, 50, 82 and 26, you can see the similar sudden jump in the proton separation energy or the neutron separation energy. So, when they are magic number, it is very difficult to separate the protons and neutrons from the nucleus because of the extra stability. So, it gave a first hint that the nucleus must also be having some cell kind of structures. So, striking similarity with the pattern of the atomic ionization energy with N or Z, it pointed towards the existence of the nuclear cell structure. In further detail, if you see this very interesting figure here, this is showing basically the alpha decay energy as a function of mass number. So, if you see here, let us say you can do many things, like for example, at a given Z, as you can see for any element, let us take ambrotium, as you see that as the mass number increases, the alpha decay energy is decreasing. Why? Because I will just come a little later in detail, but for the moment you see, imagine that at a given Z, if you are increasing A, that means what? You are increasing the neutron number. As we are increasing the neutron number in the system, keeping the proton number same, so basically you are decreasing the proton-proton repulsion. If you are decreasing the proton-proton Coulombic repulsion, so the system is gaining more stability. Okay, it is not losing stability, it is gaining stability. If it is gaining stability, its alpha decay probability is decreasing and the alpha energy is also decreasing. But what is interesting is, what you see is that when as a function of mass number, if you are looking at this curve, you see at around this value that the sudden increase in the energy of the alpha is observed when the daughter is n equals to 126, that is the most tightly bound daughter nuclei. So, for this system, like when there is a alpha decay where the daughter forms is with n equals to 126, which is a magic number, there the alpha decay energy is significantly high, you see here. So, that actually indicated towards again the magic number, existence of magic number. Similarly, if you look at this very interesting again a graph which gives the neutron absorption cross section as a function of nucleon number in different system. So, what you can observe here is also that whenever this nucleon number is there at the magic number, you see a significant decrease in the neutron absorption cross section. That also points to the cell structure of a nucleus and the existence of magic numbers. So, to that end, the first it was slowly picked up the concept of cell structure of atom, in which one of the very elementary model was Fermi gas model. So, where it is proposed that the nucleons move freely inside the nucleus like gas and interacting with a general potential field, but not with each other, and the mass density is constant, the nuclear particle density is uniform throughout the nucleus, dropping sharply at the boundaries. Constant potential, the potential inside the nucleus is approximated as a constant depth throughout the nuclear volume. Square well potential, the nuclear potential is initially modeled as a 3D finite square well potential, that is the simplest model that was assumed, and with constant depth and sharp drop near the boundary. And distinct potential well for neutrons and protons. Okay, neutrons and protons, although they are staying in the same nucleus, but because the little difference in their nature of interaction. What is the difference? For neutrons, it is only the nuclear attractive force which is governing the potential, but for proton, it is the nuclear attractive interaction as well as the Coulomb repulsion which is deciding the, thank you so much, which is deciding the interaction. So, the potential well, they are not the same for neutron and proton, so they have distinct potential well. So, if you just look at the Fermi gas model in a schematic, you can see this black line in the black diagram that gives you the neutron potential well, and this dotted blue line that give you the proton potential well. Why the proton potential well is little lifted is because of this Coulomb interaction between the proton and proton. But what is important here is that the neutrons and protons occupy energy levels in their respective potential well, and because they are fermion, each energy levels can hold up to 2 neutrons or 2 protons, so each with opposite spin, so they obey this exclusion principle. So, Now those days the question came that what kind of potential it is, what kind of potential you can use to explain this nucleus better, whether it is a square well potential or it is a harmonic oscillator potential. So it is energy that emerged by solving the Schrodinger equation does not matches with neither the square well potential nor with the simple harmonic oscillator potential. So you see the energy was solved, but it was seen that at some different number than the magic number actually you are getting these steps. So it is neither a square well potential nor a harmonic oscillator potential. So different attempts were made, out of which one attempt is like just to take this Woods and suction. They said okay, it is neither a perfect square well nor a harmonic oscillator, so let us take something in between like this is known as Wood suction potential. So when they applied that kind of potential, they actually came up with a realistic form of the cell model potential like this. Okay, it is similar to this nuclear density distribution that we shown in a few slides back, kind of Fermi function. So then they said the potential, well, it was much better to explain this. This kind of potential was much better in explaining the nuclear potential, and then the potential well must have a depth of around 35 to 50 MeV for neutrons and 5 MeV less deep for proton due to the Coulomb repulsion. But that too also alone was not sufficient, but this Wood suction potential in combination with the consideration of the spin orbit coupling inside the nucleus successfully could explain the origin of the magic number by solving the Schrodinger equation, and this actually generated the concept of the cell model, where it was assumed that the nucleus also have different energy level structure for the nucleons to fill up, and then it explained the structure of the nucleus in a better way. Now let us move to different kind of decay modes. So we have primarily alpha decay, beta decay, gamma decay, fission decay. So let us take one by one. Like for example, let us discuss the alpha decay. So why alpha decay takes place first of all? Okay. Just a moment. So as I was just mentioning slightly before, that alpha emission is a Coulomb repulsion effect. So as you see, normally you will see that the low Z elements, they do not emit alpha particle. Okay, alpha particle is something which we always observe at high mass number systems. Why? Because when we high Z systems, the proton Coulomb repulsion is very high for heavier nuclei. The disruptive Coulomb force is very high with a size at a faster rate than does the nuclear binding energy force. So the nuclear binding energy actually cannot compensate the proton Coulomb disruptive interaction, and it brings some instability in the system, and this large unstable nuclei, they wants to gain stability by decreasing size. Okay, the first thing is that they wants to decrease their size. Now depending upon the instability, whether they can attain stability by just removing a few packet of nucleons in the form of alpha decay, or if the instability is very high, they would prefer to split apart in the form of fission. But for alpha decay, it is possible to reduce little bit the size by the emission of the alpha particle, and that is why these kind of systems, they are alpha unstable. So for many isotopes of around Z is higher than 82, they are alpha unstable, and the Q is shared by the recoil energy and the daughter kinetic energy in this kind of relationship. A very interesting graph, you can see that the alpha decay energy, that is the Q value that we call, that is the energy released in alpha decay. As you plot with this alpha decay half life, you see this kind of a relation. Okay, so alpha emitters with large disintegration energies, emitter with large disintegration energies have a very short half life. And also here another thing we can see, that in a given system, as the Z of the system increases, like if you move from thorium 232 to let us say californium 250, you will see that your Coulomb repulsion increases. So that is why your alpha decay half life actually reduces. And also at any given Z, if the mass number is increasing, so the at a given Z, your then also your if the mass number is decreasing, that means you are actually decreasing the number of neutrons. So you are increasing the proton Coulomb repulsion, and therefore you are also decreasing the half life. So if you look the same Geiger-Norton law in a different kind of plot, so where you plot actually ln lambda, you remember this lambda is decay constant we discussed yesterday. and as a function of this ln of the energy, you can see this kind of linear dependence, and which shows you that depending upon the energy of the alpha, it may be varying from 4 MeV to around 9 MeV. You see that the half life changing in a huge order, like for 4 MeV the half life of thorium-232 alpha decay half life is 10 to the power 17 second. However, for polonium-212 the half life is only 10 to the power minus 7 seconds. So you can see, imagine that how sensitive it is with the energy of the alpha. So half life is very sensitive, and then the Geiger-Nuttall law is empirical and could not be explained in the beginning, but later this alpha decay model was explained in a much better way, that alpha particle is assumed to move in a spherical region determined by the daughter nucleus. So you imagine that this is my daughter nucleus. For the sake of explanation, I am considering the alpha is, let us say, here, okay, just touching the boundary of the daughter nucleus. So you can imagine that this small sphere is the alpha and this is the remaining nucleus. So when it is inside this nucleus, then it is the parent; when it is outside the nucleus, then it is just the daughter. And what I drawn in the green line is basically the potential well of the nucleus. So when alpha is reaching from this side, it is seeing a huge Coulomb barrier, and once it is inside the nucleus, it is much lower energy because it is within the potential well. But the question is, if my alpha particle is inside the nucleus, is it possible for it to classically escape the nucleus? No, because my alpha particle energy is around maximum maybe 8 MeV, 9 MeV, but my potential well, I just mentioned a few slides back, is around 30 MeV. So the barrier is very high, so classically it cannot escape the nucleus. At the same time, suppose I have a alpha outside, can I just put very easily it inside the nucleus? It also cannot enter very easily classically within the nucleus. So alpha decay could not be explained classically. In 1928, quantum mechanical theory by Gamow, Garnier and Condon came up, and they explained that, okay, you have certain energy for the alpha particle, but quantum mechanically it is always possible that if suppose you have a given alpha particle kinetic energy of this red dotted line, so at this energy, if the alpha particle is there, so these alpha particles are actually preformed within the nucleus. So by means of preformation, it has some energy release, and that energy, if it shares as a kinetic energy, so with that kinetic energy, the preformed alpha particle will keep on knocking the wall of the nucleus, the boundary wall of the nucleus will keep on knocking with a certain kinetic energy at the wall of the nucleus, and quantum mechanically there is always a probability, because it is continuously knocking up, that it may actually tunnel through this barrier wall. So the probability is very, very low. If you look at the number, for example, in uranium-238, on an average, if you calculate, the alpha particle must make 10 to the power 38 tries before it can escape. So out of 10 to the power 38 times trial on the knocking the wall of this nucleus, 1 times it may tunnel through. The probability is very, 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 very less. So that phenomena is basically the quantum mechanical tunneling. And then yesterday someone was asking that why this radioactivity is random phenomena. Now you can understand that because it's a completely random events. Like for example, if we consider alpha decay, I cannot decide that, okay, after 10 trials 1 alpha will come out. It is purely a statistical event that it is keep on knocking the wall, and there is a probability that it will come out. So that's why radioactive decay is a probabilistic phenomena. And here we come with the beta decay. So if we look at the beta decay, beta particles are just electrons which are emitted from the nucleus during decay. Now again, this is a little confusing statement. So are electrons also the constituent of the nucleus, because we are talking the beta decay from the nucleus? So how to respond to this doubt is that the beta decay can be viewed as creation of electron from the available decay energy at the moment of decay, with the electron being immediately ejected from the nucleus. So it is not that electrons are existing in the nucleus, but with the decay energy they are created and immediately escape from the nucleus. So this is different from alpha decay, where alpha particles are assumed to be preformed within the nucleus. Okay, alpha particles were already present, the neutrons and protons, everything, but they were just preformed to gain some kinetic energy to knock the wall. So different decay modes is beta minus decay, which is basically neutron going converts into proton plus beta minus and an antineutrino. Beta plus decay, which is positron to so proton to neutron plus beta plus and a neutrino, and the orbital electron is captured, so that is called electron capture. And we discussed yesterday that how the Z will move in case of beta decay in the nuclear chart. So, you can see the energy release in beta decay curve is also very interesting, have a continuous distribution. So, like alpha decay, we have a discrete energy distribution for alpha decay. I say it is 5 MeV or I say 5.2 MeV. But for beta decay, it is not a single value. You see the beta minus energy distribution, if you see, it starts from a very low value to it goes to very high value. So, that is the last point in this energy axis is called the end point energy of this beta particle, or the maximum energy share of the beta particle. And here beta plus also you can see, and that is because the concept of energy sharing between the beta and the neutrino, like beta minus and the antineutrino, or the beta plus and the neutrino, they share the kinetic energy and they get this kind of distribution. And so, the concept of this neutrino hypothesis was given by Pauli at 1930. So, it is zero charge, spin half, almost no mass, but carries away energy conservation. So, it conserves the energy, because without the concept of this neutrino, the energy is not conserved. And neutrino was observed for the first time experimentally at 1956 by inverse beta decay experiment. Now, we are almost very close to our final slides. Like if you see the gamma decay, nuclear decay mode, like most alpha and beta decays, and in fact most nuclear reaction as well, leave the final nucleus at the excited state. So, when the final nucleus is at the excited state, they get de-excited by rapidly they decay to ground state through the emission of one or more gamma rays. It is nothing but photons or electromagnetic radiation. So, you can see the typical example of cobalt 60 decay, the source that actually we used yesterday. Okay. So, you can see that 1332 or 1173 2 gamma ray, it is there for cobalt 60. So, in the practical yesterday it was used, this cobalt 60 source. So, you can see this cobalt 60 M, which is actually there, it is decaying to nickel, which is decaying to cobalt 60 ground state, and we have this as a source which we used yesterday, cobalt 60, which is basically undergoing beta decay and then subsequent gamma decay. Okay. So, internal conversion and pair production are competing process. Again, this internal conversion, pair production, I think it will be covered in more detail in the interaction of radiation with matter class. And so, these are all competing mode with the gamma decay, and there are concept of isomers like excited states, lifetime I just talked about. Now, I comes the final mode of decay that I want to discuss very briefly is the fission. So, as I said, alpha decay, beta decay, gamma decay. Fission is another mode of decay. Like as I said, if your system is so heavy that just by throwing out some nucleons in form of alpha decay is not enough to bring the stability, you need a big split, right. So, that big split is basically nothing but the fission. You just want the nuclei to split into two part or three part. So, that phenomena is fission. But in fission also, if you see that you start with some spherical nuclei, then you go from deformation and then you split. So, their kinetics basically is, if you look at the thermodynamics along the elongation axis, you see that the Coulomb energy decreases as you separate two fragments, but the surface energy increases because you are increasing the surface area. So, it goes through some kind of maxima that is kind of called the fission barrier. And if you look even more closely, like for example, if you see during the fission, you see this is your final initial stage and this is your final stage. So, the difference is basically nothing but the energy released due to the fission or the Q value, and now you have some this kind of barrier. So, you imagine that if the system Q value is less than this barrier energy, so you need something to induce the fission. Okay. So, that for example, in uranium 235 we need external neutron to actually induce this fission reaction. But there are many, you will see that they are spontaneously they are undergoing some fission, let us say californium 252. So, for that actually this barrier actually is too small that its probability for crossing the barrier same way as alpha decay, that Gamow theory, that it can actually cross the barrier with a definite probability and it can actually undergo a fission reaction. The last topic I just want to say that whenever we say radioactivity, because in radioactivity this is our last lecture in this workshop, in the application you may be many of you, I do not know if you are doing, some of you, or maybe in future you will do that, you do some kind of measurement, like either you do some nuclear reaction study or you do some kind of activation analysis study. Okay, you irradiate some sample for some time in a reactor or accelerator, take out the sample, do some counting in a detector. and wants to quantify either the maybe the fundamental properties, let us say you wants to quantify the cross section, or you want to compute the activity that is produced. So, this is a very fundamental equation what is saying that the n sigma phi, which is basically the number of target atoms that you take with, then you take the sigma, that is the cross section, phi is basically the flux of that beam, and then it is undergoing decaying during irradiation. So, 1 minus e to the power minus lambda Ti, and then e to the power minus lambda Tc, that is the decay during counting. So, what I want to give a message that during the irradiation your activity is built up, but once the irradiation is finished and you are bringing the sample to your lab for counting, the activity is again decaying. So, the time before which you started your counting, that is the T cool, and after that you started counting, during the counting also your activity is decreasing. So, you have to take care of this decay during counting. Okay. So, that way you can do some practical experiments in radiochemistry, and thank you so much for your attention, and see you in our DM.
So, any questions? The session is open for questions.
Yes, please.
Sir, in the alpha decay, if the alpha particle continuously hits the barrier, it will lose the kinetic energy, no, sir. So, it will lose its kinetic energy when it hits the barrier. Then, in order to another collision, how will it get the kinetic energy for a...
No, it will, why it will lose the kinetic energy?
If it's a, I mean a particle, if it's something means it will transfer its energy to...
It is kind of elastic, no? It is not able to transfer the energy to someone.
Is it not the elastic collisions?
It is not transferring the energy.
Okay, okay, sir.
Sir, my question is, when we discuss about nuclear density distribution, you said that it is very similar to Fermi-Dirac distribution function. But it is very sharp at the Fermi level, where we cannot see here the nuclear radius is fixed, like where we can get the density distribution is very sharp.
Yeah.
So,
can you please come again? I didn't follow.
The nuclear density distribution,
Yes,
when
yes.
we are discussing, we have said that this
Yeah, it is
is
diffused.
similarly like
Yes,
Fermi
yes,
distribution function.
Yes, yes.
But we can see their sharp Fermi cutoff for a particular energy.
Where can you see?
In the Fermi-Dirac distribution function.
No, but in Fermi distribution, if you look at this expression, sorry. Just a moment. Yeah.
Yeah, yes, sir.
So this is the expression for this distribution.
Yes,
okay?
sir.
So if you see this mathematically, if we just try to plot as a function of this R,
Yes.
you will be seeing that there is a diffused boundary. It will never be a sharp boundary.
Yes, sir.
Yeah.
But we are calculating nuclear density by assuming spherical radius,
We
right?
are assuming
Yes, sir.
for simplicity, but this is the experimentally observed.
Not exactly like
It is
Fermi.
never be a sharp boundary.
Yes, sir.
Followed, na?
Okay.
For sake of simplicity in the calculation, you
Yes.
assume that
Yes, sir.
okay. For calculating, we use a simple function R is R0 power 1/3 kind of
Yes.
function. That is for
Yes.
simplicity.
Simplicity only.
But that is the experimental real picture, that you do electron scattering experiment and
Yes,
you
sir.
get a diffused boundary for the
Okay.
nucleus.
Thank you, sir. Thank you.
Yeah.
I think for heavier nucleus the formula is okay, because the thickness of the skin is constant for all the nucleus. For heavier nucleus, I think you can assume that A equal to A power 1/3 some
For
formula.
heavier nuclei, the skin thickness is negligible.
Negligible
That's
compared to
why-
the
yeah.
size of the nucleus.
Yeah, and that's why it is reasonable to ignore that.
Yes.
Yeah.
Any more questions? Okay. So now I request Sri K. Venkateswara for feedback on this session.
Good morning, one and all. On behalf of Department of Physics, I extend my sincere thanks to Dr. Savisachi Patra Garu for delivering an insightful lecture on radioactive decay. In yesterday's class, I discussed all fundamental concepts in radioactive decay. In today's class also, Sir started his lecture with chronology of atomic history, and Sir also explained structure of nucleus, binding energy curve, liquid drop model, mass parabola, shell model, and alpha beta gamma decay. Sir lecture was highly informative, and Sir, undoubtedly your lecture inspired our students and faculty members to explore new concepts in nuclear science, sir. Once again, thank you, sir, for your contribution to this seminar. Thank you, sir.
The next session is from Sri Athanuja, and the topic is interaction of radiation with matter. Now I invite Dr. K. Bhargavi Garu to introduce Athanuja.
Good morning, everyone. I deem it a privilege to introduce Dr. Atunja, resource person of this session. Dr. Atunja joined Radiochemistry and Isotope Group, BARC, in 2014 as scientific officer after graduating from BARC Training School. He has completed his PhD in chemistry from Omi Baba National Institute, BARC, Mumbai, India 2024. Dr. Jha has completed his MSc in chemistry from IIT Madras with an institute fellowship. Dr. Jha is an university topper in chemistry and gold medalist in his undergraduation. His areas of research and expertise include synthesis chemistry, material science, radiation technology, polymer processing and modification, etc. Dr. Jha authored more than 25 papers in journals and conferences and obtained grants of 2 Indian patents. With this small introduction, I conclude and I invite Dr. Jha to deliver his talk.
Thank you, ma'am.
Hello everyone, very good morning. So in this slot we will be discussing interaction of radiation with matter. So in the first 2 days and the yesterday and today's first term, we have understood what is radiation, what kind of radiation some kind of isotope is emitting, but interaction of radiation with matter is very important to understand what is the end product, how if we place some material or some matrix under irradiation of a certain isotope, what will happen to the matter. So to understand that, interaction of radiation with matter is very important. So by the end of this session, we should be able to understand the fundamentals of radiation, its categorical variation, to know the principal interactions of alpha, beta and gamma, that is photons, and to examine the factors that affects the probability of certain kind of interaction by a certain kind of radiations. So radiation, you all know, that is transmission of energy from one place to another, and in terms of source of radiation, radiations can be categorically divided into 2 categories: natural radiation and artificial radiation. In natural radiation, there are radiation from cosmic sources, terrestrial radiation and internal radiations. And artificial sources of radiation is like synthetic radioisotope, cobalt-60, that you all have seen in yesterday's practical, cesium isotope, various radioisotope that is produced under a reactor. So those are source of artificial radiations. And then we have the Bluetooth, Wi-Fi, any kind of radiation that we are using today's day of life, that is artificial radiations. And a very common radiation, if you see, that we have present in our room right now, that is the light. The light that is illuminating the room, that is a source of radiation, but the energy is very low, that is in some EV, some electron volt, so it cannot cause any damage or it cannot ionize our skin cell. So that is in safe limits. So these all, we are surrounded by radiations. And in terms of energy, radiations are categorically divided into two parts, non-ionizing radiations and ionizing radiations. So as the name suggests, ionizing radiations means it will ionize the matter. If we put some matter in front of the radiation, in close proximity of the radiation, it will ionize the matrix. And then we have non-ionizing. So non-ionizing radiations will have energy lower compared to the ionizing radiations. That is the basic difference, ionizing and non-ionizing. And in terms of radiation processing, if you see, so ionizing radiations have more applications because it can ionize the material. So it has more applications in terms of industrial as well as in research oriented applications. So this is a small representation of how the energy of the radiation varies. Like this is our short wave radiations, and in this way the energy is increasing. So this is our infrared FTIR that we all use. Those who are from chemistry background, you may know FTIR, how it works. So its energy is lower, then it is UV visual range, then it goes X-ray, then gamma, then cosmic rays. So gamma rays having highest energy among these. So non-ionizing radiations, as I say earlier, that it does not have enough energy to ionize the matrix. It has low energy. So what comes under these radiations? Microwaves, that is a daily product we have seen, we have in our house, or you have seen in bakeries. There is a small microwave chamber, you put a food, within 30 seconds or 1 minute it will heat up the product. So this is a source of radiation. Infrared, that is a spectroscopy, FTIR, that is a source of radiation. Visible light, ultraviolet, these all are source of radiation, but these are non-ionizing radiations. Energy is not high, so it cannot ionize any matter, ionize the matrix or material if we keep any material in close proximity of these radiations. Yes? Radio waves will come into that. Yes, it will come into that. That is safe, that we use in daily life, that are non-ionizing mostly, because that you are using without any guideline, without any detector. So that means it is not has the capability to ionize anything, ionize the gas or ionize our human cells. That is why you are using it without any safety protocols. Then microwaves, I will not go in details, but microwaves is like it changes the direction of the magnetic field into some gigahertz level per second. So polar molecule, if you see some packets or some plates you cannot use in microwave. Only plastic plates or glass we can use for microwave heating, because the principle of microwave is that it interacts with polar molecule. Like there will be some separation of charge separation. Polar molecule, there is a difference of electronegative of two molecules like water. So there will be charge separation, and in change of magnetic field there will be rotation, agitation into the molecule. It is in the range of 300 megahertz to 300 gigahertz. That means in a second it is rotating the molecule into per second 300 giga time. That is why it generates heat. That is why in a very short time you can heat up your food using microwave. But its energy is very less, and it is used in for food production. Then infrared, as I said, that is energy is in the range of our molecular vibration level. So that is why in chemistry we are using FTIR to detect the functional groups. Like H2O, we have OH and OH. So this OH molecule, the molecular vibration comes under the IR vibration range, and these two resonate each another, and you can detect specific functional group using FTIR. Visible light is having slightly more energy compared to these two, and ultraviolet is having higher energy. Some high energy ultraviolet radiation can cause ionization. If you see the sunburn, if you go in a sunny day in some seashore, you will get skin will burn, you will get tanned. No? That is because of the ionization of the outer surface of our skin layer. Because of the energy is very less, so it cannot penetrate. It is only few nanometer range it can penetrate. That is why our D10, if you apply some D10 cream, or if you keep it for 7-10 days, it goes away, the dead skin goes away, because the energy is very low, but it has the capability to ionize if the energy is high for ultraviolets. Then we will come into ionizing radiation. So ionizing radiations, all our interested radiations comes under ionization range, that alpha, beta, gamma, neutron and X-rays. Mostly we will be discussing these 4-5 radiations that is having high energy, so it can ionize the matrix. Then you see, if matter you are saying, the radiations, we got some idea about the radiation, what it is and how it coming, and in previous lecture you have a good idea about what isotope emits alpha, what isotope will emit beta. Then what is matter? It is interacting with matter. So we should have a rough idea about what is what matter is. So matter is like a, if you see this room, this is a matter. Then molecule bricks of this room is like a atom. So this is a matter, then atom is constituted with nucleus and electrons. Nucleus in the center, at the center of the atom, then we have outer circle, there are electrons, and nucleus are again constituted of some quarks, up quarks and down quarks. Just in previous lecture, Dr. Patra has explained very well. So I will not go into much details. So in the nucleus, you have positively charged proton and uncharged neutron, and in the outer circle, we have negatively charged electron. So this is our matter. So any radiation interacts with matter, it will interact with these three setups, like a nucleus and outer electrons. This charge you have seen yesterday, Dr. Patra has explained this, this curve. So which isotope will emit alpha, beta, we can get to know from these curves. And this is a very preliminary slide that you all maybe have seen in your textbooks or so. It is like, it will give you an idea what is the penetration level, how far a radiation can go, alpha, beta, gamma and neutron. You see alpha, it is restricted in a thin sheet of paper. Then beta can go up to thin plates of low Z material, wood and aluminium. Then to shield the gamma and X-ray, we need high Z thick plates, thick metal plates. And for neutron also, we need water and concrete of higher thickness. So this is the penetration level. And we will understand why it is so. Now alpha, you have seen alpha energy is in some MeV, some isotope having energy of 5 to 8 MeV of energy of alpha. But why it is that our gamma is of cobalt having 1 MeV, whether alpha is having energy of 8 MeV, 8 times higher energy, but it is restricted in a thin place of paper, whether for shielding gamma we need high Z material of very high thickness. We will able to understand after this lecture. And yesterday you have seen some slides from Professor Mohapatra that irradiation of foods like mango, lychee, strawberries were irradiating with irradiations, some kind of irradiation. So what isotope, what radiation I will choose for irradiating mangoes, say for example, and what irradiation I will choose for doing a radiotherapy. Like someone is having a cancer in his outer surface, outer body. So what isotope I will choose? If someone is having a cancer in his eyes or her eyes, so what isotope I will choose? Why they are choosing ruthenium 106 for eye cancer, and for Bhavatron they are using cobalt 60 isotope. So this you will understand if you know the interaction, how it is interacting, what is the mode of interaction, and then you should be able to understand that. So this is because all the isotopes or atoms which are unstable, they are radioactive by emitting some kind of radiation. It can emit alpha, it can emit gamma, it can emit beta, and considerably we can know from that NP curve. And this is a spontaneous process as discussed earlier. So we will not go, this is the alpha. So alpha is emitted like this is an example of an alpha emitting radioisotope, that is radium-226. So if you see that proton is 88, neutron is 138, it emits one alpha to adjust the N/P ratio. So alpha radiation is like a helium with 2 less electrons. Electrons are stripped off from helium isotope. So it is positively charged. So what you know from this, that it is having a significant amount of mass because it is 2He4, it has 2 proton and 2 neutron. So compared to gamma, if you say, so gamma is massless, it is a wave only, it does not have any mass. So compared to gamma or compared to beta, it is having significant amount of higher amount of mass in helium, and it is charged also, it has 2 positive charge. So this is the main factor to determine how it will interact with the matrix. So it has having good significant amount of mass, it is positively charged. These 2 factors will come into picture in later slides, next slides. So these are some common alpha emitting isotopes. You see americium-241, isotopes of plutonium, polonium, radium, xenon, and they are used in various purposes. And how alpha interacts, because it is in charged particle to interact via Coulomb forces, Coulomb interactions with the matter. So if it come in close proximity of any material, so it will first interact with the electrons, because it is positively charged, electrons are negatively charged. So they will have attraction, they will interact with each another, it will excite the electrons to higher energy level, or it can ionize the matrix. If the energy is high, it can ionize the electrons. And in case of alpha, as the mass is high, for each interactions, alpha particle loses very less amount of energy because its mass is high. So, if you see mathematically it can be derived like for any collision maximum energy that can one alpha transfer is 1 by 2000. That means this almost 2000 number of interaction it has to go to reduce, to decay all its energy through any medium. Then Linear stopping power is defined as the energy loss per unit per length of any material. So, this is the mathematical formulation, and then there is classical expression that describes the collision energy loss of a charged particle. So, if you see this mathematical formulation, we will not go into the derivation or much explanation. If you see this B, that means the collisional loss is proportional to B, and B is proportional to, you see, that will Z of the matter. So, higher the Z, higher will be the value of B and higher will be the loss of energy. So, for high Z material, the high density material, number of electrons will be high at the outer surface. So, it will be more effective to attenuate the alpha rays. And this is the Bragg curve for charged particle. This is for alpha particle. This is also true for any charged particles. So, it is for example, for an alpha particle, you see that it is with the distance of penetration, loss of energy is plotted. So, as I said earlier, it will undergo almost 2000 interaction to lose all its energy. So, for the first interaction, energy is very high. So, the energy loss will not that much. It will go through a process very slowly, and as the number of collision increases, its energy is decreasing now. So, now I have the loss of energy will be high after a certain point, because now it has transmitted its almost half of its energy at the end of the interaction, and then suddenly it will fall down. As it needs interaction of very high numbers to reduce its energy, so the slowly it will increase with distance. So, with the increased distance of penetration, energy of the alpha is reducing. So, less the energy, higher will be the transfer. Then slowly it will increase, and after a certain point all of its energy is lost, and then there will be sudden drop. That is the explanation of the Bragg curves. And this is the particle range, how far a alpha can go. So, again that concept will come here, that is a very high mass and high Z, and it needs multiple interaction to lose its energy. That is why you see that with distance the intensity of the beam is remaining almost same to the end of the its penetration, then suddenly it is coming down. So, there will be significant difference between beta and alpha in terms of distance penetration and number of interactions. So, this is the beta particle emission of beta from 6C14. You see that it has again adjusted this number of by emitting a beta particle, it is adjusting the N by P ratio and coming to a stabler isotope compared to the initial nucleus. And in terms of beta, it is a spectrum of energy. We do not get a sharp peak. There is a distribution of energy, and we normally, if we take the energy of beta, that is average energy of beta we are talking about. So, beta particle is nothing but an electron, and as you see the low mass, alpha was of higher mass and positively charged, and beta is less mass, having less mass, and it is having negatively charged. And electron beam for accelerator interaction the same way, because it is nothing but electrons. So, interaction of electron beam will come in the next lecture, tomorrow Friday's interaction. Then we will explain interaction of electron beam and application of electron beam. That time we will understand that electron beam interacts in the same way as beta particle interacts with matter. Okay, it can very small energy, it can go elastic scattering, like Patra sir was saying, elastic scattering means it will not transmit any energy, it will just deflect upon interacting, after interaction with matter. There will be no transfer of energy. So, that is a very small energy beta particle will scatter by elastic scattering. Then for medium energy beta particle, they will go inelastic scattering, it will excite or ionize the matrix, and for very high energy beta particle, it can come close to the nucleus and it will reduce its energy, and correspondingly Bremsstrahlung radiation may emit. That is because of the, it is that is of nucleus is positively charged and our beta particle is negatively charged. So, if high energy beta particle somehow come very close to nuclear field, so its speed will reduce, so its energy will reduce. So, to compensate that energy loss, it will emit a Bremsstrahlung. That is the concept of Bremsstrahlung. Bremsstrahlung acts as a X-ray. X-ray Websterling is a kind of X-ray radiation. It is a similar to X-ray radiation. Then this is some example of common beta emitters: tritium, iodine 131, strontium, carbon 14. This emits beta, and they have applications in industrial, various industrial applications they have. And this, you see, this is the range beta particle beam. And if you remember the previous slide, how alpha particle range changes with penetration, so you will be able to understand the difference of alpha and beta, how they are reducing. It was for alpha, it was like same for quite far range, and suddenly it dropped down. And for beta, if you see, it is going same for a very short distance, and it is slowly coming down. This is the difference of alpha and beta, how it interacts. Because alpha is having higher mass, and it is having 2 positive charge. So it needs larger amount of interaction to reduce its energy. So theoretically, it has been calculated that approximately 2000 interaction it needs to reduce all its energy. So like if I am going from here to the last row of the chair, so I need like 2000 layers of interaction. So up to the last bench, last 5 bench, the energy will be similar. Then suddenly I will drop down, energy will drop down. Same thing happens with alpha. Why suddenly drop? Now it has no energy to remain. No? Now it is becoming 0. Somehow it has to stop. That is why. And this is. So now we are coming to gamma ray emission. Gamma ray is emitted as a side reaction of any beta or beta plus emission. Like you see, the cobalt 60 isotope is a very common gamma emitting isotope. It emits a beta first, and then it becomes nickel 60, that is not a stable isotope, and the nickel 60 emits gamma of 2 gamma of 1.17 and 1.33. This is the decay scheme of cobalt 60. And X-ray and gamma, there is a difference, because X-ray and gamma in terms of property and in terms of interaction they are same, but the difference is their origin, because gamma is coming from the nucleus and X-ray comes from the transition of electron from outer orbital to inner orbital. That is the difference. Otherwise, if we see here, we cannot determine which is gamma, which is X-ray. Only difference is their origin. These are some examples. Yeah, we can differentiate energy of different isotope will have different, but in terms of interaction there is no such difference of gamma and X-ray. And then we have some common gamma ray emitters, cesium-137. You have seen studies practical, those who are in group C or those who will come today, they will see cobalt-60, cesium-137, technetium-90M and iridium. These are some example of gamma ray emitter. There are many gamma ray emitting isotopes. Gamma ray emitting isotopes may have different energies and they have different half-lives. Half-life means it will become half of its initial value in what time. Just for example, cesium, it is having half-life of 30 years. That means if I have one certain activity of cesium today, after 30 years it will become half of that. Similarly for cobalt also. Cobalt is having less half-life, but its energy is high. Cobalt-60 energy is average 1.25 MeV, and in case of cesium that is 0.66 MeV. So this too is important. Why? This affects in the utilization of these two isotopes in radiation processing. In some cases, in some processing we will see that we are using cobalt-60, and in some cases we are using cesium-137. So where we need higher half-life, that we don't need to replenish the isotope frequently, but we don't need high energy, we don't need high penetration. At that time we will be using cesium-137. But in some cases where we need high penetration, we need to process large amount of material and we can afford to replenish the source after a certain time. At that time we will be using cobalt-60 isotope. So gamma ray interacts with matter through 3 primary processes, that is photoelectric absorption, Compton scattering and pair production. These 3 are the main process. This is also like a probabilistic process. It can happen together. Some part of gamma can leads to Compton, some part can go photoelectric, depending upon the energy and depending upon the material it is interacting. These 2 factors determines which way it will interact. So like you see, the photon is coming to matter, it will can have photoelectric, Compton, pair production, then they will emit some electron, it will be again interact with matter in like beta interacts with matter. Then photoelectric absorption is like photons will transfer all its energy to emit a inner shielded electron with a bound atomic electron, not the surface outer electron. It will emit a inner electron, highly well binded electron from inner cell. That is the main concept of photoelectric. The incident and the energy of the photoelectron can be written like this is the energy of the electron that is emitted, E gamma, the initial energy of the photon, minus the binding energy of the electron. This minus, if we minus these two energy, the remaining electron energy that electron will get, it will be its kinetic energy of the emitting electron after photoelectric absorption. So this you see the photoelectric attenuation is related to Z to the power 3. That means higher the Z number, higher will be probability of photoelectric absorption, and it is inversely proportional with E to the power 3. That means higher the energy, lower will be the probability of photoelectric absorption, because you see that photoelectric absorption, it is a complete absorption of the energy. So if it is having higher energy, so it may go to that probability of Compton scattering or probability of pair production will increase, because to occur photoelectric absorption, all the energy has to be absorbed by the matter. So that is why the lower the energy, higher will be the probability of photoelectric absorption. And this is just a schematic representation. You see, this is a photon coming, and this is not ejecting this atom, this is not ejecting this electron, this is ejecting the inner binded electron. This is because it can eject this electron, but then that will be Compton scattering, that will come to know in the next slide. There is a probability of ejection of this electron also, but then it will be like a Compton scattering, as by virtue of the definition, all the energy has to be absorbed and inner shell electron has to be ejected, then the photon is completely absorbed. That is why the inner shell electrons are going. Then coming to the Compton scattering, it is like loosely bounded atomic electrons will be ejected and the photon will deflected, photon is scattered with a certain angle and it will have some remaining energy. It can interact with the matter in a different way again after that interaction. This is the mathematical equation. You can see that if the photon loses least amount of energy when theta is small, that scattered angle is very small. In the next slide you see, this is the scattered angle. That photon is coming, it is interacting with the outer shell electron, it is ionizing, ejecting the electron, and then it is scattered in a certain angle. So lower the angle, you can also see from the mathematical formulation, like if the theta is 0, then this will be 1, so this will be 0, so there is no denominator. So the scattered photon energy is equivalent to the initial energy. That means it has not transferred any energy to the matrix. And if the theta is high, like theta is 180 degree, then it will be 2, cos 180 is minus 1, so it will be high, it will be high, value will be high in denominator. So scattered photon energy will be less compared to the initial energy. So higher the angle, higher will be the transfer of energy, lower will be the energy of the gamma. You can see from this, like it is coming, if there is no deflection, it will go, the photon will go like this. That means it has not interacted, and if it's transferred the most amount of energy, then there is a chance to deflect the photon in 180 degree angle or even any angle. It can deflect, scatter in any angle. So mathematically you can get to know the angle and we get to know, then that photon again can interact with other electron, like that it will process. Then the third part is pair production. So in terms of energy, if you see, so to occur photoelectric absorption, we need minimum amount of energy. Then the amount of energy if you increase, then chances of Compton scattering is increasing. Then if the photon is having even higher energy, then chances of pair production will increase. So pair production is like what happens if the minimum energy for paired production is 1.02 MeV. Why it is 1.02 MeV? Because the photon interacts in the electric field of the nucleus of an atom and it produces gamma energy of twice the rest mass of electron, then it produces one electron and positron pair. So we are creating a matter, electron and proton. So for that rest mass should be energy needed to create the rest mass. So that is 1.02 MeV. So 511 EV, keV per electron, one electron and one positron pair. So this is the minimum energy required there, but to occur this pair production we need higher amount, because there are some energy losses will be there will be some scattering. So 1.02 is the minimum energy that is needed to occur pair productions. Like see, if it comes closer, the energy is very high, that is why it is not deflected by the electrons. Otherwise, it would have done photoelectric absorption or it would have done Compton scattering. The energy is very high, so it is coming very close to the nucleus, and now it is emitting one positron and one electron. So, at the energy is creating matter, so minimum energy required is for the rest mass energy conversion, that is 1.02. So, this is a curve of dependence of gamma ray interaction with atomic number and photon energy. So, you can see the chances of photoelectric effect is very high if photon energy is less, that you come to know from the mathematical formulation also. It is inversely proportional to e to the power 3, and then Compton's effect is dominating in energy from 0.1 to up to 10 MeV, and pair production, the minimum energy requirement for pair production is 1.02, but the chances of pair production is increasing if we if we cross the energy more than 10 MeV. So, in some very common isotopes like cobalt for say or cesium, the energy of cesium is 0.6 MeV, energy of cobalt is 1.25 MeV. So, in most of the cases the most probable interaction of gamma is Compton scattering, because of see this part, if you see, it is coming in the range of 0.1 to 10 MeV, this range. So, most probable interaction of gamma ray is Compton scattering. Then there is neutron. Neutron can interact by elastic scattering, inelastic scattering and radiative capture. I will not go much detail for neutrons, and like it can combine in some cases some prompt gamma can be emitted. Then probability of interaction depends upon energy of the neutron and identity of the target nucleus. Like for fast electrons, then it will become thermal electrons, then after considerable amount of energy loss, it can be captured. Energy wise, if you see, so neutron categorically can be divided by thermal electron, the energy is 0.025 eV, then slow neutron, then intermediate energy neutron, then fast neutron. Some example of some reactions of neutron is capture reaction. In case of this, you see 1H, it captures one neutron and emits one gamma. This is the N-gamma reaction, you can call it N-gamma reaction. Then it can emit some charged particle also by capturing one neutron, like 32S, it captures one neutron, it emits one proton. Similarly, 10 boron can capture one neutron and it emits one alpha. And fission is the most used example of neutron, for like in previous presentation you have seen that application of fission, some very large uranium, thorium, large molecule, then it will fission has to be done to come to stable isotope. So, in that case neutron accelerated the process in doing fission of that isotopes. So, that is all for my side. If you have some questions, you can ask.
So, the session is open for questions. If you have any.
Sir, in pair production, that please, you are saying that electromagnetic radiation means gamma ray is interact with the electric field.
Gamma
The
ray?
first line.
This one?
Next one, next slide.
This one?
Previous one, sir, previous. Back. A photon interacts with the electric field of the nucleus of an atom.
Yes.
So actually photon is nothing but electromagnetic radiation.
Yes.
So how it will influence the electric field?
Because nucleus is overall, if you see, so overall nucleus is positively charged, and our electromagnetic radiation, gamma is electromagnetic radiation. So if it crosses the nuclear field, it will have some deflection, it will interact with the nuclear field. No?
Okay. In general, we are saying that means whenever the electromagnetic radiation is going on.
Yes.
So if you apply in the electric field,
Yes.
inside the electric field, if you pass the electromagnetic radiation, it will not deflect, right?
No, that is normal electric field of normal value. This is a nuclear field.
Okay.
The dimension is different, no? Values is different. The scale of field, electric field is different in case of here.
Okay. Okay, sir.
Yeah, but because the nuclear size is in fermions, right? It's very close, 1 by r square, right? Electric field value. So it affects. It's very close, very, very strong fields.
number of hertz. Okay. Yes. Yes.
See, initially with the photon energy increasing,
Yes.
what is the sir? That
With photoenergy
photoelectric
increasing.
effect starts increasing, sir.
Yes.
So it dominates up to some level.
Yes.
And it is later Compton effect starts to dominate.
Correct.
Yes, sir.
Yes.
And after that, pair production. See, sir, it is decreasing.
No, that is means separation. This is not the probability. In that range, pair production will dominate.
So that graph means
This is the this comparison, separation, phase separation kind of thing. Okay. Yeah. It's and it's
Any
slowly
questions from
increasing
students?
because it needs to have the ionization energy at first. It needs to at least have energy higher than the ionization energy of the material, of matter. Then only photoelectric effect will happen. That is why it will increase first. But this plot is not showing the probability or the rate. This is just separation of these three incidents.
So this pair production is it the only process where radiation can be converted into matter? Is there any other process where radiation can be converted into matter?
In synchrotron or in cyclotron, we can use radiation to produce matter. In some cases of very, very high energy.
Okay.
Okay.
So if you don't have any question, then we'll thank Tanuja for his very insightful talk. Now I request Dr. Harinath Reddy garu for his feedback.
Good morning all. I am very privileged to propose vote of thanks to the speaker, Dr. Atanuja, on behalf of participants and organizing team. Sir has covered during this lecture what is the radiation and sources of radiation, and also sir covered ionizing and non-ionizing radiations, how they will interact with the matter also sir has covered very briefly. Thank you, sir. And also sir has covered very briefly gamma ray, how it interacts with the matter differently. So sir has briefly covered three effects, so which we have discussed now. The low energy one is photoelectric effect dominance, and the middle of energy Compton effect, Compton scattering will cover. And if you go for higher energy, sir also briefly explained how pair production will happen. So sir has already covered how this radiation will interact with the matter, and also sir has briefly explained how neutron radiation also interacts with the matter. Thank you, sir. You briefly explained us and make us understand more briefly. So on behalf of participants and organizing team, once again we will say heartfelt thanks to the speaker, Mr. Dr. Atanuja, sir. Thank you, sir. Thank you.
Thank you, Dr. Harinath Reddy garu. Now we'll have the third session of today's technical parts, that is career opportunities in DAE by Dr. P.S. Ramanjaneyulu garu. Now I request Dr. B. Gaurunayudu garu to introduce Ramanjaneyulu sir.
Thank you, sir, for giving this opportunity. Dr. P.S. Ramanjaneyulu garu joined BRC in 2003 through BRC training school OCS 46 batch. He obtained his masters from Andhra University in 2002 and PhD from HBNI in 2012. He has been involving in chemical quality assurance of various nuclear materials related to FBTR, PRB and modified APS, ARA, and other DAE programs. Dr. Ramanjaneyulu involved in determination of hydrogen deuterium in pressure tube materials of IPH and WRS for their lifetime management. He is very actively involved in indigenous development of various analytical instruments which are used for the sequia of different materials with respect to non-metallics. He also involved in development of ion selective electrodes for various ions of the interest in the nuclear technology. He is the recipient of DAE Special Contribution Award and several DAE Group Achievement Awards. He is having about 100 publications in peer-reviewed journals and symposia. With this brief introduction, I am inviting Dr. B.S. Ramanjalan sir for his lecture.
Thank you, Gauri Naidu garu. From last 2 days, maybe you are listening so many things about the DAE and their applications, and now today morning onwards, or maybe yesterday evening onwards, maybe you are learning something fundamentals of radioactivity decay, then how the decay is happening, how it is interacting with matter. Now I just want to change your attention to some other direction. That is, I just want to explain what are the career opportunities in our DAE. Why we have to popularize that we require something manpower, because if you see the evolution is a continuous process. Maybe you can see in the old and very old movies, the Suryakantam garu used to sit in one chair and someone used to do the hand fan, the whistle karra, right? No, that at that time it is a luxurious thing at that time. The later you have seen the fans, that is also one, at that time it is a luxurious, because just someone has to switch on the fan, then you will get the air. The later the air coolers, now the AC, air conditioner, window AC, split AC, now inverter AC. The evolution is a continuous process. This evolution is continuous process not only in the technology, the human mind also. Definitely you are much smarter than us, because there is a generation gap. Now if any organization have to prosper, we require the new brains. Now we have to attract new people and make the awareness what are the career opportunities in our DAE program. That I want to highlight here. What was my plan of my presentation? The introduction and brief history, because how the DAE is evolved from the beginning onwards, I want to explain there. And what is the DAE mandate, and then DAE centers of excellence and deliverables, then DAE recruitments like OCS, DGF schemes through BRC, and the training schools like BRC training school or AMD training school, and then BRC doctoral programs. We have the one HBNI institutes like Homi Bhabha National Institute, where the people can get the PhD, they can enroll into the PhD program with their stipend also will be provided, and some of the practical training project like and internship at BRC. This one by one I will explain in the next coming few slides. Okay, the history, what I am saying, the great visionary that Jahangir Homi Bhabha, his own words is like this: it is the duty people like us to stay in our own country and build up outstanding schools of research such as some other countries are fortunate to possess. Means at that time there are some western countries, they have the lucky to have the highest greatest research institutes at that time. Now he thought that now we have to initiate these research institutes in our own country. That's what he thought at that time. And then Bhabha is the first Indian to receive the Adams Prize, and he was awarded Padma Bhushan in 1954 and nominated for the Nobel Prize for the physics in the year 1951 and also 53, 54, 56. But why he is not got, that is a different issue, but he has been nominated for the Nobel Prize. In the beginning, the Homi Bhabha founded the Tata Institute of Fundamental Research, that is the TAFR. You must have seen this TAFR about this in the Mumbai. On the 1st June 1945, with support from the Sir Dorbaji Tata Trust to fulfill the vision. He is actually the Akkagar Abbai, Tata Gariki Manalada Namatan, Baba. Then he got the funding from the Manamama, then he instituted the TAFR Institute. Okay. The institute was first began functioning with the Cosmic Ray Research Unit of the campus in the Indian Institute of Science, Bangalore. The TAFR was first started in the ISC Bangalore. The latter he shifted to the Kennel Fort building. This is the Kennel Fort building, sorry. Okay, it is just like that. Maybe anyone may be knowing that about the Ambani building in Mumbai, Antalya. So adjacent to that, this Kenilworth building is there. That their TFR is first started. The latter shifted to the TFR new buildings. That is also we can be seen in the Mumbai, if anything, one of the highlight research institute in the Mumbai. The latter, the Atomic Energy Establishment Trombay was started. The government of India has created this AET in 3rd January 1954. Now, the way they will get the manpower for this, the scientists and engineers who are engaged in the reactor design and development and instrumentation, metallurgy and material science, they all are gathered, selected from the TAFR and then started the AET. Whereas the fundamental, who are doing the fundamental science in the TAFR, they left over there only, who are working on the technological part, they are taken to the AET and then he started this atomic energy establishment. Now, so like our Bapu Gar is the famous cartoonist in our newspapers, the same way the R.K. Lakshman is a very famous cartoonist in the national papers, where he is described about this Nehru is initiating, the Nehru is riding the one buffalo cart, Edlabandi, where the common man is sitting here with the wheel of nuclear energy, means with the limited resources, by using the advanced technology, Prime Minister wanted to guide the nation like common people. At that time he described about the AET formation. Why he mentioned like that? Because we have the very limited finances, because we just got the independence at 1947, we don't have very much financial resources at that time. Then also the limited scientific and technological manpower, because at that time the education, the level of education is so poor, we don't have any well educated or well established technologies at that time. The technology ban regime, because the nuclear technology at that time, not only at that time, now also the technology is not completely available for all of us. Still they have the restrictions, embargo problems are there. Then the inadequate industrial and manufacturing base. See, if anything is, we want to establish anything, we require the supporting technology to get it from some industries. At that time also we don't have any industrial support. Then extremely small resource of fissile materials. If you want anything, reactor, start the reactor, anything, we require like uranium. At that time the processing, identifying that nothing is available. Everything has to build up from the scratch. The vision and determination is the leading force to make this all nuclear energy. The atoms are today are making great journey to serve the nation. At that level onwards he started, and today what we are saying that we are applying to the food industry or agriculture anywhere. Today we have reached this level and started from the scratch. Now, the marching steps from early days to now, as I mentioned, the first DAE started at the OIC building, Old Age Club, that also belongs to actually Tatas, and they are donated to our AET at that time. Now it is headquarters for our DAE. From this building, now that is the starting point here. Now you see the entire India, each corner we have the DAE institutes. In our own Andhra Pradesh also, now they are constructing one new campus for the BRC at near to Visakhapatnam, Achutapuram. And if you see the neighbor state, Telangana, we have the NFC, that is nuclear fuel complex in Hyderabad, and Manuguri heavy water plant is there. Like this, if you see any state, definitely there will be one DAE institute will be there. From that point, now we are spread to this level. The why nuclear energy? See, there are so many options are there, like hydrogen energy is there, wind energy is there, tidal power is there. Then why we have to go for the nuclear energy? Maybe as yesterday P.K. Mohapatra has already mentioned, looking at the modest lifestyle, we require power consumption at least 2000 kilowatt hour per year. We see it's not only power consumption is only like what we are required for our sufficient, for daily users. This is the indicator that how much of power you are consuming means how much you are technological advanced stage. That if you get it anything modest lifestyle, we required of this, and then that means the total India required 3400 terawatt hour per year. That much energy we required. If you see the all realistic evolution of renewable energies is expected only 1229 terawatt hours per year. Now if you see the shortfall of 2171 terawatt hour a year, will need much higher growth and input from the nuclear energy. The why it is only nuclear energy? For such large requirement, all sources of energy have to be deployed. We can see not only the nuclear energy, we have to see all other things also. The presently, the 86% of electricity needs are met by burning coal or oils. However, the coal or oil option has severe global impacts on environment and commerce, in addition to the huge infrastructure needs. As yesterday already Mahapatra sir already mentioned, the 1 kilogram of uranium-235 if you see, that is equivalent to almost 3 metric tons of the coal. Thus much huge amount of is required, and also because of all the global impacts, the environmental changes, we can't go for this coal or oil to meet our requirements. We have to see some other options. That is the best option is, one of the best option is the nuclear energy. You see the climate changes impact. The first one here, if you see the glaciers, around 1780 it is a depth of our Himalayan glaciers. Now it is continuously deteriorating. Now at the 2001 it is almost this year. These all are happening because of all global warming. If you continuously burning this coal and oil, that may be further deteriorate. If you increase the 1 meter level of sea level, on the mean level of sea level is increased to 1 meter, the many coastal parts of our India will be merged into the sea. And also if you see the abnormal conditions that are like heavy rains, or some of the places are drought conditions, these all are happening because of the climate changes. Now we have to see the other options. For that, the nuclear energy is one of the best options. The various application of atomic energy, it is not only the only power generation. If you see the nuclear energy is a wealth generation as well as the quality of life. You see the electricity, as I mentioned, the nuclear power, and it will be also can generate the fluid fuel substitute, because of burning the oil and other things can be substituted by using nuclear energy. And also some of the technology can be transferred to the water purification. And also you see the food industry, health industry, environment, national security, technology and industry. The why I am saying the technology, if you see at any time at 1962 onwards, the highest turbine at that time is 100 megawatt, and today 1000. The both are generated only in the DAE only. The technology also, the nuclear energy will be in the Indian, from the Indian side, if you see, they are all in the #1 stage in the technology wise. DAE centers of excellence and deliverables. The Department of Atomic Energy have the different sectors. The one is the power sector, that is ruled by the NPCL, that is Nuclear Power Corporation of India Limited, Mumbai, and Bhavani Kalpakam. And for any power sector, any technology sector, we require one R&D support. For that, we have the R&D sectors where the BRC Trombe, IGCR Kalpakam, RRCAT, that is Raja Ramanna Center for Advanced Technology, Indore, VCC Kolkata, and Atomic Minerals Division, Hyderabad, and GCNAP, Bahadurgarh in Haryana. And also we have the industry mineral sectors, that is like NFC Hyderabad, Heavy Water Board, and BRIT, like that. Public sector like UCL and ECAL, RERL. Now everywhere we are using the voting machines for EVM machines. These all are fabricated in the ECAL Hyderabad. Then if you see, although we have the service organizations like DCCM, DPS or GSO, like aided institutes, we have several institutes, aided institutes are there from the DAE, like the TAFR, SINP, there are so many things are available. The milestones along the journey, the first Apsara nuclear reactor, that is constructed in 1956, that is the first nuclear reactor in the Asia at that time. And we have 2 more research reactors in Dhruva and Cyrus in our own BRC campus. And very recently in 2018, the Apsara U is already commissioned. And now there are other research reactors like Purnima, Jarlina, Kamini and HWR. These all Purnima were research reactors to demonstrate the plutonium as a fuel in the nuclear technology. And the Kamini, that is the reactor is available in our Kalpakam, where the 3rd stage of Indian nuclear program is demonstrated. And the HWR critical facility, this advanced heavy water cooled reactor, that is demonstrating the thorium technology. These all are different types of reactors are available in our DAE. Now, what is the option? There are so many ways are there. We are not followed what the well established international accepted route. We are followed the closed nuclear fuel cycle, where because of our limited sources, we have taken the uranium from the mines and converted into the oxide and gone to the conversion to the nuclear fuel pellet, has gone to the reactors where the irradiation will be done. After that, we have gone to the reprocessing plant where it could separate the uranium and plutonium. The plutonium again it has gone to the nuclear fuel sector and it will go to the reactors. And now from the waste also we are separated the many important products like fission products that could be used in agriculture, industry or health sectors. Now and then what are the remaining waste is there, that will be waste vitrified and it will be storage. If you see for this conversion, as Dr. Mahapatra already mentioned yesterday, if you are running 1000 megawatt electrical power stations in the year, it will maximum generate about 40 meter cube of waste. Whereas in the same amount, if you have to burn the coal, it will be generate the huge amount of ash as well as the CO2, NO2 gases. The waste wise also we are generating very less. That's what it is very environmentally friendly. With indigenous technology, innovations and societal applications of nuclear energy, closed fuel cycle is the boon. The expansion of Indian nuclear energy program, then these are the data I got it in 2023. There are 23 reactors are there with a capacity of 7480. Now maybe all people are listen about our budget proposal, where the Nirmala Sitharaman is declared by 2047. Now the power, nuclear energy power has to be gone to the 100 gigawatt. At present we are less than 10 gigawatt. Now they want to increase with the span of 22 years, the 110 times. Okay, that means that we require a lot of manpower to boost our nuclear energy. The already reactors are sanctioned for about 10 reactors, 700 megawatt electricity or 10 PHWRs. The additional NPPs, the nuclear power plants proposed to set up with the foreign collaborations like VVR, that is a Russian technology, and EPRs with the French collaboration. The research reactor for radioisotope production in public-private partnership is also proposed in Ahmedabad. There are so many proposals are there that the sky is the only limit for our any manpower is requirement. The commercial production of nuclear electricity from the last 5 decades, you see the remarkably safe operation of Indian and nuclear power plants. From the last 50 years, we never had anything accident or anything leakage from any nuclear reactor. We have a very safe records, and you see the power production rate is also, you see, from the end of 1972, it is continuously progressing. Now within 22 years, it will progress with much faster rate than what we have seen here. The continuous safe and reliable operation of more than a year has so far been achieved by 35 times by Indian PHWRs. If you see the Kaiga power station continuously operated 962 days, that is one of the world record. And we have the NAPS, Naroda Atomic Power Station, that is 852 days. Now if you see the order wise longest operation of any power reactors, that is India only created the history. We have the longest operating years, that is one of the world records. Now you see the BRC, what is happening in the BRC. Now BRC, if you see the support the power program, we have to do the R&D to support the power programs, and we see the R&D for the healthcare and medical sciences, and we also do some R&D for the food and agriculture side to increase the shelf life or agriculture high productivity, and also you do the research isotopic hydrology for the water resources, and then also we will see the industrial applications. This already we will discuss in the coming few days. The glimpses of R&D activities at BRC. See, if you see the engineering discipline, the joining the dissimilar materials means there are two different type or multiple types of materials can be joined together. This research is going on in our BRC, and generating the metallic glasses, because we have to handle high amount of radioactive materials. We have to see what type of operation we have to do, but at the same time we have to stop what the radiation is coming from them. Then we have to develop the metallic glasses. Then corrosion studies, these all nuclear plants are operating at very severe conditions, very high temperature and high pressure. The corrosion rates will be very severe there, and then we have to do some corrosion studies also there. Then high voltage pulse power techniques, as our Atanu Jha already mentioned, for generating cyclotron or anything, we required very high voltage pulse power techniques. The high integrity software design and verification, because many of the things experimentally is not possible, we have to do something simulations, then we require software and design and other things. The nuclear and imaging instrumentation, like our any healthcare, if you want to see anything, how the tumor is formed, how the tumor is growing, these we all required images, the nuclear and imaging instrumentation. The semiconductor radiation detectors, now when you want to see the radiation, how it is there, how much it is there, then we have to develop the detectors also. The magnetics and gravity design, cavity design, the control systems for nuclear reactor and accelerators. If you are generating any nuclear reactor, how to control and all R&D base has to be there. And cryptography, trusted platforms, because because of national security part also, we have to see something code generation where it cannot be reached where it should not be reached, then we have to generate something code to maintain our national security. This all being done in our BRC with engineering discipline. Now if you see the chemical sciences, we are supporting the nuclear fuel cycle, starting from the milling to mining to up to the waste management. The chemical sciences play a very key role here. Then you see the nuclear chemistry, where our Sabishachi Patra is working on the nuclear chemistry for the estimation of various radioactive elements by non-destructive methods. The nuclear materials, we have to develop something new types of advanced nuclear fuels. Then that's R&D is being done by in the chemical sciences department. The energy materials, in addition to this nuclear energy, some of the people are also working on the hydrogen storage materials. We can see that they like complement each other, hydrogen energy or nuclear energy, because we have the very long plans for the generation of hydrogen by using nuclear reactors. Some of the people are also working on that. And the catalytic materials, if you see catalyst materials we are being developed for like hydrogen production and other things. The functional materials, materials for environment, suppose some of the people are also working for the CO2 problem is there, that can be converted as the energy sources. The computational chemistry, hybrid materials, materials for hydrogen energy and analytical chemistry. See, in the BRC we have the one modular lab, maybe anyone, some of the maybe people have visited. The people have the say like that word, if you have anything doubt, from one corner you start, by the time you reach the another end of modular lab, you will can clear your doubt. Means in all types of fields there are experts are available. If you approach them, any type of any scientific problems, you will get the clearance from them. What I want to say in the chemical sciences or any type of branches you see, you can identify that any type of problem, there are some persons will be there in BRC who is working on that field. The physical sciences, the high energy particle physics, the high pressure studies, thin film, multilayer and single crystals, and soft matter and nanomaterials, magnetism and crystallography, the entity testing, sensors, thermoelectric materials, multiferroics and functional materials. There are physics people also, they are working on the different directions. Solid state physics, these are special branches are there in our physical sciences also. Then the biological sciences, the anti-cancer research, there are how to avoid this cancer, any possibilities there are like that people are studying. The molecular biology, that includes that disposal of any waste by using without adding any chemicals, how to decompose your waste and other things. The trombe mutant varieties, there are around 62 varieties are developed by radiation mutation in BRC. The food technology, the how to preserve the food without spoiling it. The plant tissue culture, the biocomposting, bioremediation, the global transactional biofilm mustard. There are so many types of works are being conducted in all the discipline, including your biosciences. The neutron beam national research facility, we have the Dhruva reactor, there are the neutron beams are available. If any UGC or any university people are approaching, they are ready to collaborate with them. About 200 users are already used in our neutron beam technology in the Dhruva reactor. The advanced magnetism and crystallography studies being done in collaboration with various universities. The dynamics of functional materials, soft matter and nanomaterials, thin films, like that. We are always ready to collaborate with various academic institutes. The trombe crop varieties, as I mentioned, about 62 items are there, from the ground nut to the jute. These all are radiationally mutated, some breeds they are using. They have the better qualities than what the conventionally available. The food irradiation, as already Dr. P.K. Mohapatraji already mentioned, the food irradiation is also going in big way. Now because if you want to export anything without any irradiation, the people will not accept. You see the mangoes, the initial period, because of shelf life is very small. If you want to export to any US or anything, we have to go only by flight. But now because of these irradiated mangoes, the shelf life is increased so high, then we can transport by using like sea route, by ship. Even though it will take more time, but the cost wise it will be very less. That's what the farmers can get the better benefits from this. The trade through sea route is advantage because it has the reduced cargo charges, almost like 1/8 to 1/10 compared to the air freight. The more quantum can be exported as the availability of containers is not a limiting. If you want to go by flight, maximum for 1 kilogram maybe they are charging 600 to 800 rupees, whereas in the cargo that price will be very low, and also we can generate the huge amount of mangoes can be exported. this radiation can application to various directions. This is one of the example I mentioned here. You see the quantity metric ton wise from the 2007 to now 2022, from 157 to around 1086 metric tons being done for irradiation and exported. The Babatran for the cancer therapy in the healthcare sector, it is indigenously made in our DAE, the Babatran, where by using the radiation they can cure your cancer tumors, and also we are exporting to, giving to the donation to various countries, third nations, where the photo is showing that PM Modi is donating to instrument to some other African countries. Then multi-leaf collimator, this all technology has to be transferred, because the tumor will not be like a particular shape like rectangular like that, it will be shape will be the different shapes. Now only we have to target only the tumor part only for the irradiation purpose, then we require different types of collimators. This all being done in our DAE. The Nisargruha, whatever the biomass we are generating like food waste and other things can be used for the generating the biogas that will be used in our again cooking. We have the one training school hostel complex in our Anshit Nagar. The whatever the waste is generated in the training school hostel and other canteens, that will be used for generating the biogas, and the same gas they are using for the cooking purpose. And the isotope hydrology, as yesterday Mahapatra sir already mentioned, they regenerated the several springs in our Uttarakhand region. The isotopes imaging the urban waste like the sludge hygienization, yesterday already discussed. The industrial applications, again it will be discussed by Atunuja tomorrow. The mega projects, there are like eye on the gamma ray scale, but largest, the 21-meter diameter telescope in the Asia, and second largest in the northern hemisphere at the highest altitude. In the Ladakh, they are initiated this telescope, and the solving the cosmological mysteries like a nature of dark matter and energy, and total mass of the universe, gamma ray horizon. These all discoveries can be done by using this telescope. In addition to the project, like a mega science project is also being connected by DAE. The Vizag BRC campus, it is in our own Andhra Pradesh. There they are proposing for the high flux research reactor, the quantum computing, 40 MeV proton accelerator, 20 MeV electron accelerator, Subir Crystal Technology Center. These are being planned in our Vizag plant. The mega science projects, ITR, we are in the part of IT, International Thermonuclear Experimental Reactors, that is the nuclear fusion future reactors. India is also part of CERN project, LIGO and Fermilab collaborations, INO, the Indian Observatory, Neutrino Observatory, that is being planned in our Tamil Nadu. These are the mega science projects. Not only in BRC, we want to see the entire DAE. There are what are the glimpses of R&D activities, other R&D units of DAE. This is IGCR. Basically, the IGCR mostly working on the second stage of our nuclear energy program, basically the fast breeder technology, the fast reactor physics and engineering, the advanced fuel fabrication and processing and reprocessing, condensed matter physics and chemistry, high entropy alloys and microstructural evolution, analytical support for the reactor operations, simulation and assessment of radiation damage, corrosion science and technology, recovery of strategic materials from fast reactor spent fuel, coral facility. These all are facilities are available in our IGCR Kalpakam. These are same thing again they are explaining here. There are different discipline people are working in this IGCR. The manufacturing technology development at the IGCR, because for the second stage of nuclear program, the fast breeder reactors, the various materials are being developed indigenously in IGCR. The RRCAT indoor, that is the Raja Ramanna Center for Advanced Technology. The nanomaterials for quantum technologies, the single crystal ceramics and carbon aerosols are for various applications. Development of front ends and beam lines for industry 1 and 2. Your professor Dr. Gauri Naidu also done some of the studies in RRCAT. Fundamental beam dynamic studies, superconducting RF cavity development, oxide nanoelectronics, plasmonic materials, so semiconductor composites. There are so many types of studies are being carried out in the RRCAT indoor. The synchrotron beamline facilities at RRCAT, high intensity X-ray beams are available. There are so many things are available on the physical science side. These are the R&D activities at RRCAT. RRCAT is the forefront of the charged particle accelerator research with round the clock running national SRS facility. Apart from this, we are also the forefront of laser technology research. That developing the various lasers that will be used for the national security also. We have an excellent technology incubation program where advanced industrial accelerators, cryogenic systems are under incubation in partnership with industry, and there are so many programs are going on in RRCAT. So what is the future trust area for the RRCAT side? HBSRS, LIGO projects, electron LINAC, proton accelerators, high energy lasers, quantum technologies, laser additive manufacturing, precise fabrications. These are the future trust areas for the DAE as well as RRCAT. And considering the expanding programs at RRCAT and other DAE units in the area of accelerators and lasers, and also the international collaborations in this area, there is a strong need to train officers of physical sciences, electronics, mechanical engineering discipline, specifically in the area of accelerators and lasers. This is a LIGO VECC, where the variable energy cyclotrons are being developed for the medical applications. AMD, because we require all nuclear materials, they have to explore how many mines are there in entire India. There are different ways they will approach for the identifying our ores. The major uranium provenances like our Tumbalapalli, that is near to the Kadapa, the one of the largest mines are identified in for the uranium. Okay, what they will do, that survey and prospecting the resource development for uranium, thorium, all for rare earth elements, assessment, evaluation, categorization of uranium ore reserves. This all studies being carried out at AMD. They will do the survey. First they will take what the detectors you are using, GM counter type of detectors, they will fix on the aeroplane and they will run with lower altitude. Then from the gamma ray, what are emitting from the uranium sources, uranium ores, they will identify the source. After that they will do some small mining and they will assess what is the quality of your ores. This all studies being done in our AMD, the headquarters at our Hyderabad. These are the technologies what are being done in our DAE. Now I will go to the career opportunities, how to enter to the DAE programs. The DAE offers excellent career prospects, cutting edge and interdisciplinary R&D activities. Like you see, it's not like that what engineering means they will do only for engineering side. We have the multidisciplinary research collaborations, engineering and chemistry, life sciences, physics. There is maybe the place, only the place in entire India where the all disciplines works together with good collaborations. Okay. The nuclear technology is the knowledge intensive. The nuclear power plants produced about 778 million kilowatt hours of electricity. The needs well trained human resource and strong industrial infrastructure for its exploitations. The nuclear power provides about 50% in the America clean energy, and in the case of France it's maybe more than 60%. The nuclear energy is the most reliable energy source in America, needs multidisciplinary approach to the problem solving. Nuclear helps power 28 US states and requires safety analysis encompassing the entire gamut of engineering and health related safety issues. Why we are mentioning that US, it is not like that only India is only going for the nuclear energy, like advanced countries like US or France, everywhere they are going for the nuclear energy. Okay. Therefore, hire and train approach, we are producing to produce industry ready manpower, practicing the professional as the induct faculty, then tacit, explicit and implicit knowledge is transferred. Over 11,000 people have been graduated so far through our BRC training school. That may be the next person may be one of you, it may be from you also. The recruitment program to the DAE through OCS, that is the orientation course for engineering graduates and science postgraduates, and another one is the DGFS, the program for the BRC training school, like BRC training school will be. Notification is already declared. If anyone wanted to approach, you can see that BRC websites in the student where career opportunities are there, they all is described there, how to enter to the OCS program. The recruitment scheme in BRC training school, the orientation course as I already mentioned for the OCS, the 1 year orientation course for engineering graduates like BE, BTech or anything BS engineering, then our 5-year integrated MTech, and science postgraduates in BRC training school Mumbai and Hyderabad for geology and MD. Along with the training, they will also get the stipend during this training program. After the successful completion of this OCS program, they will be absorbed in the BRC, and also at the same time they will also get the MTech degree from the HBNI. And eligibility criteria, further details you can get it from the www.brcocsexam.in. I am requesting you all kindly visit this website to get these full details of about the OCS program. We have one more program, the DAE Graduate Fellowship Scheme, to who are engineering graduates, to who got the admission in IIT Mumbai or IIT Madras. They will also get the stipend from the DAE to further their upgradation of their knowledge. The latter they will be absorbed in BRC as a scientific officer C. Okay. For those who are selected for BRC training school and also secure admission for MTech in IIT Bombay or IIT Madras in one of the relevant MTech program or specialization, they can be absorbed in DAE. The paid stipend from the tuition fees from MTech from the DAE side, and there will be joint guideship for the, because in the second year they have to do some project work where the one of the guide from the DAE institutes, another guide is from the IIT. They have this type of programs. Okay, in the case of mechanical engineering, what the different disciplines are there. I mean, you can see these all details in our website. These all are given very detailed manner in our website. I am requesting you all kindly see this. Of anyone who knows who are doing this type of studies, you kindly advise them to visit our website and then make it more awareness about our DAE opportunities in our DAE. The eligible disciplines, I mean in the case of physics, there are different branches are there, these all are mentioned here, and in the case of chemistry, bioscience, geology, this all you will get the information from our websites. Okay. The eligible disciplines for the DGFS, in the DGFS scheme they have special branches, thermal fluids engineering, thermal engineering, these all details are also mentioned in our website. Kindly go through this, and then if you have anyone is kindly inform them. Okay. Yeah. The 1957, it is also actually, I want to say that it is initiated by Dr. Homi Bhabha, because at that time there is no skilled manpower is not available. That's what he initiated this training school program, such that it can generate the skilled manpower here itself, and that can be used for the progress of DAE. These are the different disciplines, and what is the process? The stage 1 screening, either gate score or online test. If you are qualified the gate, then from the you can directly apply for the interview, or otherwise they will conduct the online test, written exam test, and then if you qualified for that, then they will call for the interview. It maybe will happen in month of May or June at 2025 at BRC Training School Complex. Here they will use third year normal tier fair will also given who are attending this interview. Okay. The maximum age limit is only 26 years by August 1, 2025 for the general category. For the other categories, what are the age relaxations there as per the government rules, it will be done for them also. Okay. The eligibility criteria for the for engineering side, either they have to qualify from the to who are qualified with GATE 2023, they can also apply now, or maybe who are qualified 24 or 25, they will fix something percentile cutoff. If they are qualified for that, they can attend directly for the interviews, they can apply directly there, or otherwise they have to apply appear for the written exams. These are eligibility criteria for the physics discipline. They can, for science also we have the two approaches. One is the directly for GATE qualification, or we have to qualify for the written exam, and they can appear for the written interview, and the minimum 60% marks is required for the getting appearing these exams or selecting to the up to the interview. These all details maybe you can get it from our website, bioscience. Okay. I just want to mention in the during the training period what the amount they will get it. The monthly stipend about 74,000 per month, and at a single time they will provide about 30,000 rupees for the book allowance. They can purchase what the books they require, and also accommodation will be provided training school hostel, and that is the one of the period we can enjoy our life, because there are still now also we will not say that we are studied in this year like that. We are always the batch number like that. See, I am from 46 batch, our Sabhichachi Patra from 54th batch, Atnuja is from 57th batch. The batch number will be tag will be there for our entire career. And the structure of course, like nuclear related, about 30% will be there in the 1 year orientation course. And the chemistry specific, like our any discipline specific, will be 30% will be course has to be completed. And 12 weeks project will be there. And also we are giving some vacations also with the paid stipend. And training and evaluation. The training program consists of regular lectures, practicals, projects work and evening lectures. The coursework is divided into 3 semesters that are called trimesters, and examinations will be conducted after the completion of the course for the performance assessment. The TSOs with minimum aggregate marks equal to 50% based on the first attempt of all examinations would be only considered having successfully completed the course and will be appointed in the grade of SOC. In this training course, we should get at least 50%, then only will be absorbed as a faculty, employee in our DAE program. The DGFS course, again the stipend will be the same, 74,000 rupees, and then because they are studying in some other places, they will be given 60,000 rupees for the book and other things, and 4 lakhs also given for anything, any equipment or during this project if they are required. And then accommodation is mandatory for the where they are studying, like IIT Madras or IIT Powai, they will get the accommodation in their respective IITs. Okay. After the absorbing as a SOC in the DAE, about approximately 1,35,000 rupees will be salary will be given, including all allowances such as leave travel LTC, leave travel concession by air. The every year up to first 8 years subject to conditions, they will be given to LTC for every year, and after that once in a 2 years. The children education allowance and an annual professional update allowance are also payable, and we have our own schools. If you want, they can study there itself, and what are the fees we are paying, everything we will get it back. A comprehensive contributory health service scheme, HS facility is there, we have all the medical facilities, and there your dependent family members also can get these all medical facilities. And absorbed as a Group A Gazette Officer, the Government of India, on the post of Scientific Officer C, except in the case of PSUs where service rules of the corporations apply. I mean, like R&D institutes like BRC, IGCR, they are the Gazette Officers, whereas in the commercial units like NPCL, the scale remaining everything will be same, but they will not be considered as a government Gazette Officers. The BRC Training School merits, thus these are selection of meritorious and motivated engineering graduates and science postgraduates, and then we are hiring and we are giving the training, and then continuously this program is continuously happening every year. So far about 11,000 people already graduated so far from the BRC training schools. These are the training school hostel, and these are the HBNI that is also have the training school in our BRC Anshita Nagar campus. Okay. The earlier days, these are the training school complex where we did our training program. These are the recent one that's constructed in our Anshita Nagar. Okay. The bring all selected candidates from the why we have to give the course of this orientation course. The aim is to bring all selected candidates from different universities to a common level of understanding through the foundation course, because someone is maybe coming from Bengal, someone is coming from Andhra, Tamil Nadu, like that. They have different type of learning scales. You combine together, maybe because of mutual interactions, they can share their ideas and they can exchange the knowledge, that such that a common platform will be created. And now because of this 1 year course will be helped us for any type of problem, we will see that in that division any batchmate is there or not. If any batchmate is there, we can approach very easily because of we have the bonding, training school bonding. That is what they started this orientation course, to impart the multidisciplinary training in the core courses relevant to the nuclear industry, to impart training in the frontier areas of science and technology in respective disciplines through advanced courses like this. Okay. The OCS different disciplines from different branches of engineering and basic science like physics, chemistry and bioscience. These are the number of students so far graduated, the highest number in the mechanical, and the bioscience and RSC are the maybe the smallest number. That they all depending on the what is the manpower requirement. Now the HBNI, in addition to the as a permanent faculty member, we also one more channel is there to enter our DAE, to serve in DAE. There is a HBNI, that is deemed to be university, is a research university and educate students to the doctoral and master's level and pursue the research in accordance with the mandate. It is a basic as well as applied research programs are available in our HBNI. Who are want to do the PhD, they can approach, they can enroll into the HBNI program, and this all available in our HBNI website. Okay, this is the website www.hbni.ac.in. The employees of Department of Atomic Energy have the opportunity to pursue higher studies with Homi Bhabha National Institute. So who are employees in our DE program, they can go for like PhD or MSc or master's degree. DE not only provides employment opportunities but also takes care of their future growth by giving them opportunities toward the full realization or research potential, and there are so many ways are there to get the enrollment, increase our qualifications. The Homi Bhabha National Institute have the different institutions are there in this HBNI umbrella, like BRC, IGCR, the Institute of Plasma Research. There are different types of institutes are there in the umbrella of HBNI. And BRC doctoral program, the DDFS, DAE doctoral fellowship scheme in the engineering. In the case of science disciplines, we have the junior research fellowships. Okay. In the case of DDFS, who are pursuing PhD under the aegis of HBNI, they inducted to the one of the following constituent institution of HBNI like BRC, IGCR or IOP or VECC. The qualifying degree and other academic qualifications are like that, who are done the MTech or BTech, and then they have to qualify some written exam and then they will be enrolled into the PhD programs. And who are employees, they will have the separate committee and they will screen it, then they can approach for the PhD, they can enroll into the PhD program. The age limit, if you are approaching directly for the PhD program, the age should not be more than 28 years, and then fellowship will be given about 80,000 rupees per month up to the 4 years, and if your guide is recommended, they can extend to 5th year also, and during this period you will get the degree as well as your salary also, 80,000 rupees per month. The BRC doctoral program in sciences, and the selection criteria is the minimum 60% in the aggregate in the BSc as well as the MSc level, 55% in the MSc level. Student with all scores are like CSR net or anything GATE, or also we will conduct the separate entrance test for the HBNI doctors program. Who are selected for this, they will conduct the interview and then they will be enrolled into the PhD program for the HBNI. The fellowship will be given for 37,000 rupees per month, and then single attempt they will give 60,000 rupees per year to see the something books or whatever is their requirement. Okay. The BRC doctors program in sciences, there are about how many screened out, the percentage by they are receiving, how many are appear for the interview and other things. The practical training projects, internship at BRC, they can approach into the HRDD, like this website we can follow that www.brc.gov.in/student. They have all the career opportunities, and in the month of 23 itself you see that 23 they have given the data. The so far about 1051 approached, and out of that 858 people are already got this internship. That shows that how much of significant percentage, about more than 80%. Then any one of you can approach for any internship, they can get the practical exposure of what is the DAE technologies. The first, the continuing education program, like being any faculty members, if they want to give something, some lectures on their interest of topic, they can approach our HBNI or HRDD, then they will have some committee, they will screen it, then they will deliver these lectures also. Finally, the come and grow with us. We are welcome you all and join our DAE program and grow along with us. You get associated with the prestigious organization founded by Dr. Homi Bhabha, and then you inherit the strong and competitive team in frontline R&D sector. The department offers an attractive pay structure, incentives and awards and meritorious performance. You can also enhance your academic career by acquiring higher qualifications such as PG diploma or MTech or PhD program. Then I will stop my presentation here. I welcome you all to visit our website as well as enroll into our BRC programs, a training school program, or different schemes are available. You can consider these are the one of the career opportunities to enter to DAE. Thank you.
Thank you, sir, for a very informative presentation.
I can answer if any queries are there.
If you have any queries, students, particularly this is very useful to you. So if you have any doubts how to enter into
We just want to
BRC,
get the awareness about the how to enter to DAE, and then the same time why you have to enter, have to give some justification. That's what I've given this all first 20 minutes presentation about where, what the different technologies are being developed at DAE. That's all. That is what my aim. And in addition to this, we also have the scientific assistants, category 1 trainees, another way of approaching to the DAE enter with the BSc qualifications. They even have higher qualifications also, there is no problem. The minimum qualification is the BSc or diploma in the case of engineering side. And we have one more, one is a category 2, that is either ITI or +2 equivalent, that is the minimum qualification. And recruitment is happening for every year. You kindly go through our websites, there are so many career opportunities are there. In the case of training school program, there will be no reservations, only the age relaxations are provided, but remaining all as per the Government of India rules, the reservation rules are applied. But only in the case of training school program, there is no reservations, only age relaxations will be provided. If anything further information is required, maybe you can interact during our lunch time. Any of, not only me, any one of our resource persons could be contacted. That's all. Thank you.
That's so nice of you, sir. Yes. Yeah. So thank you, Dr. P.S. Ramanjanayulu garu. So you explained about the history of TIFR and then AAET, how we began very humbly, then various departments and sectors of DAE, and then how these sectors are creating a lot of opportunities, and also you encouraged the students to join in these sectors. You also explained in various departments like engineering, chemical science, physical science, biological science, and other different sectors where there are endless opportunities, so that the students can actually go through the website and then see where you can fit into. And then I encourage all the students, please go through their website, and meanwhile while the workshop is going, and you can also actually meet the resource persons. The scientists actually have lots of experience. You can meet them and get the information. So I encourage all of you to join in these great projects. Thank you very much, sir. Now there will be a small session, interaction with resource persons. So they will be asking very fundamental questions based on the talks happened so far. So those who answers will be getting prizes. So get ready, students.
Good afternoon, everyone. This session is particularly for students, not for faculty. In case of no response, okay, in case of no response from students, faculty can give the answer. Okay, these questions are from slides presented by our colleagues, Patraji or apne Atanuja, and yesterday our director जो भी present किए हैं. From those slides only these questions, fundamental and basic questions. I'll ask question, raise your hands, I'll select from one, okay, and give the answer. No group answers, okay. The first question is, this is very, very fundamental question. Who discovered radioactivity first? Who discovered radioactivity? Oh. Yes.
William Röntgen X-ray, sir, and then Henry Becquerel, sir.
Henry Becquerel is the right answer. Tell your name and institute.
Vandana sir from Andhra University, Visakhapatnam.
Please come. Next question. Which is the India's first nuclear reactor? India's first nuclear reactor. That person. What's your name? Please come. Right answer. It's
Gopal
Apsara
Krishna.
is the India's
Apsara
first
is the right
nuclear
answer.
reactor. Next, one more basic question. What is isotone? Isotone, what is isotone? Yes.
Isotones are which having the same number of neutrons in it, na? Of the same
Yes,
species.
yes, correct answer. What's your name?
My name is Simrat and I am come from Delhi.
Okay, right. Congratulations. The next question is, cobalt-60 undergo beta minus decay, right? So what is the decay product? I repeat, cobalt-60 undergo beta minus decay. So what is the decay product after beta minus decay? Beta minus decay. What happens when one isotope undergo beta decay? That madam.
Nickel.
Nickel? Isotope.
60.
Nickel 60 is the right answer.
Please be fair, madam. Monica ma'am, please accept the present.
When an element undergo beta minus decay, it will go to next element. But the mass will be same.
I am Jayman Monica, lecturer in physics, Government Degree College, Chintalapodi. Thank you.
The next question is from yesterday's presentation. Which radioisotope is called workhorse? Which radioisotope is called workhorse? It is from yesterday's presentation. Anybody? Workhorse for radiopharmaceutical.
Anyone from faculty members?
Faculty members? Milking, yesterday sir told milking. And this element is not available in nature.
We know already. Technetium.
Technetium 99M.
M. Yeah, it's metastable
Okay,
technetium.
this is a workhorse. It is the most. It is used for most of the diagnostic purposes in nuclear medicine field. The next question is, what is half-life of radioisotope and what is the relation between half-life and decay constant? What is the half-life of radioisotope?
T half equal to 0.693 by lambda.
What is half-life?
What is half-life?
What is the meaning? half-life name itself suggesting.
అంటే తెలుగులో
తెలుగులో చెప్పండి, నో ప్రాబ్లం.
అంటే ఏదన్నా ఒక డీకే గనక హాఫ్ లైఫ్ అంటే జరిగిందా ఒక హాఫ్ భయం వేస్తుంది.
చెప్పండి, ప్రాబ్లం లేదు, చెప్పండి. మీకు
హాఫ్ లైఫ్ అంటే అంటే ఏదన్నా ఒక రియాక్షన్ జరిగినప్పుడు డీకే జరగడానికి ఒక అంటే ఫుల్ టైం కాకుండా ఒక హాఫ్ టైంలో మనం మొత్తం టీ హాఫ్ అంటే T0 నుంచి టీ హాఫ్కి వెళ్ళిన మధ్యలో అంటే 800 న్యూటన్స్ ఉన్నప్పుడు ఒక 400 ప్రోటాన్స్ జరిగినప్పుడు ఆ మధ్యలో ఉన్న టైంని హాఫ్ లైఫ్ అంటాం.
Your explanation is very vague, but you got the point. Yeah, you can go and take.
Formula is right. What's your name?
Banu sir.
Bhanu. Come. Please. T half is equal to 0.693 upon lambda. Now I will explain what is T half.
My name is Sri Rama Banusri and I am from Government College Autonomous Rajahmundry. I am studying MSc first year.
Now T half means any radioisotope is having 1 curie activity and it decays to 500 millicurie, half of the activity. The time is required to become a half. The time is called T half. Next question is, stable radioisotope having which type of distribution of nucleons? Oh, no group answers. No group answers.
Please raise your hands.
Please raise your hands and give the answers. Okay, you.
Here. Yes, even
Yes,
distribution.
it's the right answer. What's your name? Can you tell why it is even?
Even means there are two unpaired single particles are making pair. That's why they don't have any chance to pair up with other nucleon.
Okay. Please come forward.
Accept your. The even name because of the pair formation. Me pair. You are from?
Andhra University Nuclear Physics.
She is from Andhra University Department of Nuclear Physics.
The next question is, binding energy is a measure of what? Binding energy is a measure of what?
Binding energy per nucleon or binding energy?
Binding energy. Okay. Binding energy per nucleon is a measure of what?
Yeah.
It's a measure of nuclear stability.
Yes, excellent answer. What's your name?
My name is Kavya Tanushree Reddy, sir.
You are
and I am
from?
from Adikavananaya University.
AU, Andhra University.
Adikavananaya University.
Okay, Rajahmundry. Congratulations.
Thank you, sir.
The next question is, what is the energy of thermal neutrons? Thermal neutrons. You have already given one answer, na? Anybody? Thermal neutrons, yeah.
0.025.
What unit?
MeV. KeV.
No. MEV, KeV. Thermal neutrons. What is the energy of thermal neutron? Number is right, but unit is. Okay, no problem.
Yeah, you can go. At least you remember the number,
Okay.
right?
Right, what's your name?
Adil, sir.
Adil. Okay. EV. It's a 0.025 EV.
EV, okay, sir.
Name from where you are coming.
Okay, sir.
Name and?
My name is Adil. I am from Nuclear Physics Department, Jnanananda Laboratory for Nuclear Research from Andhra University.
Okay. Congratulations. Next question. What are the advantages when we irradiate the food with radiation? When we irradiate the food with radiation, what are the advantages? Any advantage?
Half-life increase అవుతుంది సార్, increasing the half-life, which means a long period of preservation period increases.
Yes, that is shelf life.
Shelf life,
not half-life.
Sorry.
Any other?
Some it's also kills some bacteria inside that
Yes, yes.
food
Okay.
materials, some other.
Sprouting it.
Yes.
Sprouting it's. Please tell your name. Please come forward.
I am Mohan sir. I am from Andhra University, sir.
Congratulations, Mohan.
Thank you, sir.
Andhra University guys are leading. Next is when the radioisotope decays by beta minus and beta plus, it always accompany with what? When any radioisotope undergo beta minus and beta plus decay, it always accompany with dash. With what? Beta minus beta plus తో పాటు ఇంకోటి వస్తుంది, అదేంటి?
Anyone from this side? Those who already got are not allowed.
Beta minus, sir.
బీటా మైనస్ బీటా ప్లస్ తో పాటు ఇంకోటి వస్తుంది, అదేంటి?
Beta.
Last.
Yeah, you can try.
Neutrino, antineutrino.
Yes, exactly. Correct answer. Congratulations. Please come forward. Tell your name.
I'm Pranita from Arts College.
Full పేరు చెప్పు.
I'm Pranita from Government College Autonomous, Rajamundry.
Department of Physics or Chemistry?
Department of Physics. I'm studying first year
First
MS.
year MSc. Okay. Congratulations. Ready for next question? The minimum energy of gamma ray required to form a pair production. Minimum energy required for gamma ray to form a pair production.
She already got.
Already.
She already got. Okay.
1.02 EMVs. MEV.
MEV. Okay. Right answer. 1.02 MEV required to form pair production. What is pair?
My name is M. Lakshmi Devi, Government Autonomous Rajamundry. I am studying
Congratulations.
MSc Physics.
What is that pair? పేర్ ప్రొడక్షన్ కోసం 1.202 MeV కావాలి, రైట్? వాట్ ఈస్ దట్ పేర్? ఆ పేరు ఏంటి? పేరు కాదు, పేర్. ఆ 2 particles ఏంటి? ఓకే,
It is electron and positron. Please tell the pair name. Electron and positron.
Electron and positron.
Electron and positrons are the pair. The next question is, radioactive decay follows which order of kinetics? Which type of kinetics? Chemical kinetics చదివి ఉంటారు మీరు డిగ్రీలో. సో రేడియోయాక్టివ్ డీకే అనేది ఒక ఆర్డర్ ఫాలో అవుతుంది. అదేంటి? ఏ ఆర్డర్ కైనెటిక్స్ ఫాలో అవుతుంది రేడియోయాక్టివ్ డీకే?
You both got already.
ఇక్కడ ఇక్కడ ఇక్కడ
Random process, bro.
No. Which order of kinetics followed by radioactive decay? అది random process, okay, but కెమికల్ కైనెటిక్స్లో ఆర్డర్స్ ఉన్నాయి. బీఎస్సీలో మనం చదివాము. కెమికల్ కైనెటిక్స్లో రేట్ ఆఫ్ రియాక్షన్లో మనం చదివాము. నో గ్రూప్ ఆన్సర్స్ ప్లీజ్. నో హింట్స్ బై ఫ్యాకల్టీ ప్లీజ్.
Second order, sir.
Anyone else? No, you already got. Students. You're a student or faculty? Okay.
First order.
Right answer. First order. Radioactive decay follows first order kinetics.
Why it is first order?
What's your name? Mike lo చెప్పండి.
It's first order. It's starting range to.
How we decide the order of reaction?
First order, second order difference. Yes, sir. It's a higher order level starting from. I am from Durga Satish, Nana University, Rajahmundry.
Congratulations. So the last question. How many ways gamma ray interaction with matter? How many ways gamma ray interacted with matter? Last law come. Last bench.
Three ways.
What are they?
I don't know.
3 ways is the right answer. So what are they?
First అయితే లేదు కదే నేను ఆయన ఎక్స్ప్లెయిన్ చేశారు మాకు అది గుర్తుంది.
చెప్పండి తెలుగులో చెప్పండి ఏం కాదు.
సారీ సార్ నో ఐడియా. అది 3 అని తెలుసు అంతే.
3 is the right answer. We didn't ask the question of name, right? Only number.
Please come forward. 3 ways are photoelectric effect, Compton scattering and pair production. 3 ways. Tell your name.
My name is Soumya and I'm from Adikavi Nannaya University campus, Tadepalligudem, Department of Physics.
So congratulations to winners.
Thank you for the participation.
So these kind of quiz will be every day at the end of the morning session, okay? Which indicates that how the participants are attentive to the lectures and what the knowledge that you have, okay? Which so that you should, it is like writing get things that what you have supposed to be listening during the session is very important. It is a good practice. Try to write down the things what you are listening in the sessions, and try to go and to the room or houses and try to know what are the things which are related to what the sessions that we have given in the like technical program. Okay, if you like before coming to the sessions, if you understand something the basic related to that, so you can betterly can understanding the sessions what the like our like scientific officers are supposed to be discussing on that. If you come with a blank mind, so you feel everything is difficult. That is the main problem with the students. They simply coming with with the bags, but they don't do any prior work to before coming to the attend these lectures. So my suggestion is to go to the, so after your homes or rooms or wherever you go, just try to know what are the things which are related to the list of the lecture title that we have given in the technical program. So then it is very easy to you to follow the things. Even you may not notice the time. Okay, when you feel hard means you don't know anything related to that relevant topic. That is only the basic difference. If you feel bored, it is okay. So next day onwards, then I hope that you will be coming with very good basics, and you try to know what the things supposed to be delivering by our scientists. Okay, so thank you. So afternoon session we will be having our hands-on experiments in the lab that what you had already done in the yesterday. Okay. So today we do not have any kind of lecture within the seminar hall, okay, in the afternoon session.
You know the groups, right?
Maybe.
For today your groups will be changing.
Groups are same, we are changing the experiment is changing. So I have to share the image anyway.
Yeah. Could you please display this again? Maybe they will come to that they have taken photo. Acha.
The group B will be done doing the experiment number 1. See, experiment 1 will be done by group B, then experiment 2 will be done by group C, and experiment 3 will be done by group D. Right now? Yeah. And then experiment 4 will be done by group A. Okay?